Picture yourself walking in a straight line forever and never hitting a wall, but also never looping back to where you started. Sounds impossible? NASA scientists say this might be exactly what our universe is like, and they're closing in on proof that will change how you see reality forever. Today, we're diving into the shape of the universe. Flat, infinite, or curved in on itself. I'm breaking down what it means for space to have a shape at all, and how something can be finite, yet have no edges. Stick around, because this isn't just abstract thinking. It's a cosmic detective story with real clues we're finding right now. Here's the mind-bending problem. We're stuck inside the universe, trying to figure out its shape from the inside out. Imagine being an ant on a balloon, trying to figure out if the balloon is round or flat without ever seeing it from the outside. That's our situation. For centuries, humans thought space was just a big empty box with stars pasted on the walls. Then Einstein showed space itself can bend, twist, and curve. But how? And what does that even mean? NASA scientists have been wrestling with these questions for decades. The challenge? We can't step outside the universe to look at it. We have to find clues hidden in light from distant galaxies, in the afterglow of the Big Bang, and in the way gravity behaves across cosmic distances. It's like solving a puzzle where all the pieces are scattered across billions of light years. And here's the kicker. The answer could mean the universe is finite, but has no edges, like the surface of a sphere, but in 3 dimensions. How is that even possible? That's what we're here to unpack. So what do scientists mean when they talk about the shape of the universe? They're not talking about some container holding the universe. They're talking about the geometry of space itself, the rules that determine how lines behave, how angles add up, and whether parallel lines ever meet. On Earth, we live on a curved surface. If you walk in a straight line on Earth, you're actually following a curve. If you could walk forever in one direction, you'd eventually end up back where you started. That's because Earth's surface is finite, but unbounded. Now imagine that in 3 dimensions. Could our universe be like that? Finite in size, but with no edges? Or could it be infinite, stretching forever in all directions? Or could it be flat, like an endless sheet of paper? These aren't just philosophical questions. They have real answers that scientists are hunting for. To understand this, we need to talk about 3 possible shapes for the universe: flat, closed, and open. A flat universe is like an infinite sheet of paper. Parallel lines never meet. Triangles add up to 180 degrees, and space extends forever without curving back on itself. A closed universe is like the surface of a sphere, but in 3 dimensions. It's finite. You could theoretically travel across it and end up back where you started. But it has no edges. In a closed universe, parallel lines eventually meet, and triangles add up to more than 180 degrees. An open universe is like the surface of a saddle, curving in opposite directions. It's infinite. Parallel lines diverge, and triangles add up to less than 180 degrees. But how do we figure out which one describes our universe? NASA scientists are using several clever methods. One way is to look at the cosmic microwave background radiation, the faint afterglow of the Big Bang that fills all of space. This light has been traveling for about 13.8 billion years, since the universe became transparent. By studying tiny temperature fluctuations in this light, scientists can detect the imprint of the universe's geometry. If the universe is curved, it would act like a lens, distorting the apparent size of these fluctuations. If the fluctuations appear a certain size, the universe is flat. If they appear larger, it's closed. If smaller, it's open. NASA's WMAP satellite, and later the Planck satellite, have mapped these fluctuations in incredible detail. And what they've found is surprising. The universe appears to be flat to within a 0.4% margin of error. That's shockingly flat. But here's the thing. Measurements this precise still leave room for a slight curvature we haven't detected yet. And even if the universe is flat, that doesn't necessarily mean it's infinite. It could be finite, but unbounded in a way we don't yet understand. Another way scientists probe the shape of the universe is by studying the distribution of galaxies and galaxy clusters. In a flat universe, matter should be distributed in a particular way. In a curved universe, gravity would cause matter to clump differently. So far, large-scale surveys of the cosmos show a distribution consistent with a flat universe. But again, there's room for error. There's also the method of standard candles. Objects with known intrinsic brightness, like certain types of supernovae. By measuring how these objects appear dimmer than expected based on their distance, scientists can infer whether the universe's expansion has been affected by its geometry. So far, these measurements also point to a flat universe. But here's where it gets really interesting. Even if the universe is flat, it might not be infinite. It could be finite, but unbounded in a way that's hard to visualize. Imagine a video game world that wraps around. If you go off the right side of the screen, you reappear on the left. Our universe could be like that in 3 dimensions. If you traveled far enough in one direction, you might end up back where you started. Scientists call this a multiply-connected universe. It would be finite, but have no edges, just like the surface of a sphere, but with a different kind of geometry. NASA scientists have looked for evidence of this by searching for circles in the sky, patterns in the cosmic microwave background that would indicate the universe wraps around on itself. So far, they haven't found convincing evidence. But the search continues with more sensitive instruments. Another mind-bending possibility is that our universe is just one of many bubbles in a vast multiverse. Each bubble could have its own shape, its own physical laws, and its own destiny. In this scenario, the shape of our particular universe might be determined by the conditions during its birth in the Big Bang. The shape of the universe is also connected to its ultimate fate. If the universe is closed and finite, gravity might eventually halt the expansion and cause everything to collapse back in a big crunch. If it's open or flat, the expansion might continue forever, leading to a big freeze where stars burn out, galaxies drift apart, and the universe becomes cold and dark. Current evidence suggests we're heading for the big freeze scenario, but new discoveries could change that picture. What makes all this so fascinating is that we're talking about the fundamental nature of reality. The shape of the universe determines what's possible and what's impossible. It affects whether time has a beginning and an end, whether space goes on forever, and whether there are other versions of you out there in a vast cosmos. And here's something to wrap your head around. Even if the universe is infinite, we can only ever see a finite part of it. That's because the universe has a finite age, about 13.8 billion years. Light from beyond a certain distance hasn't had time to reach us yet. The observable universe, the part we can see, is about 93 billion light-years across. But the whole universe could be much, much larger, possibly infinite. Scientists are also exploring whether the shape of the universe might have changed over time. In the very early universe, just after the Big Bang, space might have been highly curved. Then, during a period of rapid expansion called inflation, it might have been stretched so flat that any curvature became undetectable. This inflation theory solves several cosmic puzzles and is widely accepted, but it's still being tested. But the most mind-blowing discovery NASA scientists have made: the universe appears to be flat, not just in 3 dimensions, but in 4-dimensional spacetime. Einstein showed that space and time are interconnected, and the curvature of spacetime is what we experience as gravity. When scientists measure the geometry of the universe, They're really measuring the curvature of spacetime itself. And here's the kicker. The flatness we observe is incredibly precise. If the early universe had been slightly more curved, it would have recollapsed almost immediately, or expanded so fast that atoms could never have formed. The fact that it's so flat, what scientists call the flatness problem, is one of the biggest mysteries in cosmology. It suggests there's something fundamental we don't understand about the Big Bang and the nature of space itself. Some scientists think this flatness is evidence for the multiverse. Our universe is just one bubble among many, each with different properties. Others think it points to new physics beyond Einstein's theory of gravity. Whatever the answer, it will revolutionize our understanding of reality itself. So the shape of the universe remains one of the biggest mysteries in science. Current evidence suggests it's flat, but with room for a slight curvature we haven't detected yet. It could be finite but unbounded, or truly infinite. The answer has profound implications for the ultimate fate of the cosmos and our place in it. NASA scientists continue to probe this question with ever more sensitive instruments, looking for clues in the light from distant galaxies, the afterglow of the Big Bang, and the behavior of gravity across cosmic distances. What they find will not only solve a cosmic puzzle, but could also reveal new laws of physics and reshape our understanding of reality itself. In the stillness of a clear night, under a canopy of stars, it's easy to imagine a beam of light traveling straight and true. You point a flashlight at the sky and picture its narrow ray slicing into the darkness forever, unbending and unwavering. This idea of a straight line feels simple and absolute, but in the vastness of the universe, where space itself can curve, what does it really mean for a path to be straight? If the fabric of the cosmos is warped or bent, even the straightest possible route might eventually loop or curve along with it. We call such a path a geodesic, the closest thing to a straight line when space isn't perfectly flat. It's the route a light beam or a spaceship would naturally follow if undisturbed by anything, simply cruising along the shape of space itself. To understand this, imagine you are an ant walking on a large balloon. To you, the ant, the surface seems flat beneath your feet. You set off in what feels like a straight line, never turning left or right. Eventually, much to your surprise, you find yourself back where you started, approaching from behind. The balloon's curved surface guided you in a great circle all the way around. You never felt yourself turn, yet your path was curved by the shape of the balloon. In our universe, a geodesic is like that straight-line path on a curved surface. If the universe itself is curved, perhaps wrapped around into a giant sphere-like shape, then a light beam shot into the depths of space might one day return to its origin. It could come full circle through the cosmos. It sounds like a strange, almost mystical possibility, that a telescope peering into the distance could, in theory, catch a glimpse of our own galaxy from the back. On a smaller scale, we've seen how gravity bends light. In 1919, during a solar eclipse, astronomers observed starlight curving around the sun's edge. The star wasn't where it appeared to be. Its light had followed a curved path through the warped space near the sun. That was local curvature caused by the sun's mass, a dramatic demonstration of Einstein's theory of general relativity. But what about the universe as a whole? If space on the grandest scale is curved, light traveling across cosmological distances would subtly betray that curvature. Two beams of light, launched side by side, aiming into the void, might not remain side by side. Given enough time and distance, the shape of space could draw them together or push them apart. In a universe with positive curvature, one that bends like a sphere, those light beams could gradually converge, like lines of longitude meeting at Earth's North Pole. In a negatively curved universe, more saddle-shaped, the beams would drift away from each other, diverging more than they would in a flat expanse. If the universe is perfectly flat, they would stay parallel forever, never meeting, never parting more than when they started. These cosmic path experiments are not just thought games. They hint at real tests we can imagine. Consider shining a laser out into space, and another one in the exact same direction. In a flat universe, the two laser beams, no matter how far they travel, would never meet. Always equidistant, like railroad tracks on a straight stretch. But in a closed, curved universe, those beams might slowly bend toward each other until they intersect, even though neither beam ever bent in its own local frame. It's space itself, curving. In an open universe, the opposite happens. Space fans out, and the beams separate more widely as they go. We don't have a lab big enough to do this experiment directly, of course. The universe is our lab, and we rely on nature to run the experiments for us. Light from distant galaxies, crossing billions of light years, is our test beam. Its journey carries the imprint of the space it traverses. As we observe it arriving here, we can search for clues, subtle distortions or patterns, that reveal whether it traveled through a cosmos that is curved or flat. In this way, straight lines in the night become clues to the universe's shape. A ray of starlight, bent and stretched over eons, whispers to us about the space it moved through. If we pay close attention, we might discern whether that space is gently curved inward, spread outward, or not curved at all. But to truly read those whispers, we need to think bigger, to construct shapes out of light itself. The simplest shape we might try to draw on the canvas of the cosmos is one of the first every child learns: the triangle. And the tale of the triangle in space has its own secrets to reveal. Imagine for a moment that you could string giant straight lines between galaxies, like drawing a triangle on the canvas of the sky. Picture choosing 3 far-flung galaxies as your triangle's corners. Now, shine a beam of light from each galaxy to the next, connecting them in a triangle that spans millions or billions of light years. If you could ride along one of those beams, you'd go in what feels like a straight line, aimed directly at the next galaxy without turning. Eventually, you'd arrive at your destination, then perhaps hop onto the next beam and continue until you'd visited all 3 and returned to where you started. You would have completed an enormous triangle out in space. The big question then arises: what is the sum of the angles inside this triangle? In our everyday world, every schoolchild learns that the angles inside a triangle add up to 180 degrees, a simple truth of flat geometry. But that truth is only guaranteed on a perfectly flat surface. On a curved surface, the rules change. For instance, if you draw a triangle on Earth's surface, say using lines of longitude and the equator, you can easily get an angle sum greater than 180 degrees. Take the classic example. Start at the equator and walk straight north to the North Pole. That's the first leg of your triangle. Then turn and walk down to the equator along a line of longitude. That's the second leg. Finally, follow the equator back to your starting point, the third leg. Each turn you made was a right angle, 90 degrees, because you went from the equator up to the pole and then from the pole back to the equator. You've created a triangle with 2 corners at the equator and 1 at the pole, and all 3 angles are 90 degrees. Add them up. 90 plus 90 plus 90 equals 270 degrees, far above the flat 180. The Earth's curved surface gave this triangle extra angle, revealing its positive curvature. Now consider the opposite, a saddle shape, which curves the other way. Imagine drawing a triangle on a saddle or a mountain pass. its angles add up to less than 180 degrees. The surface dips and spreads so that your triangle's corners are more acute than they would be on a flat plane. The sum might be, say, 170 degrees or some value under 180, depending on how strongly curved the saddle is and how big a triangle you draw. These examples show the principle. In a space that curves one way, triangles gain angle. Curve the other way, triangles lose angle. So if we could measure an enormous triangle in the universe, the sum of its angles would be a direct clue to the cosmos's curvature. More than 180 degrees would hint that space has a positive closed curvature like a sphere. Less than 180 would suggest a negative, open curvature like a saddle. And if, somehow, the angles come out to exactly 180, we'd be living in a flat universe, or at least one where the region of the triangle is too flat to show any difference. This sounds like a wonderfully straightforward test. Draw a cosmic triangle and measure its angles. In practice, of course, it's fiendishly difficult. We can't exactly stretch measuring tape across galaxies or carry gigantic protractors to distant stars. Even so, the idea of it is illuminating. It tells us that the geometry of our universe is not just an abstract concept. It's something that, in principle, could be measured by simple means, if only our tools were large enough. In the 19th century, the mathematician Carl Gauss reportedly attempted a terrestrial version of such a test. He measured the angles between mountain peaks with precision instruments, trying to detect if the sum deviated from 180 degrees, which would have hinted that space itself might be slightly curved by gravity or otherwise. His results, within the accuracy of his day, found no deviation. On the scale of a few dozen miles, space appeared flat. But on the scale of billions of light years, who knows? The universe might reveal a different story. Since we can't hop between galaxies with rulers in hand, astronomers have devised other clever ways to test the cosmic geometry. One indirect way to perform the triangle test is to use light itself as both the connecting line and the measuring tool. Imagine sending a flash of light from galaxy A to galaxy B, another from B to C, and a third from C back to A. If you record the directions of these incoming flashes when they reach their destinations, you effectively have the angles of your giant triangle. The beauty is that the light will naturally travel along geodesics, the straightest possible routes in space. So the path of each beam is the leg of the triangle, and the angle at each galaxy can be inferred by the orientation of the arriving beam compared to some reference direction. In a positively curved universe, those beams would arrive in directions that indicate a sum greater than 180 degrees. In a negatively curved universe, the orientations would sum to less. This thought experiment, while beyond our technical reach, reinforces a key point. Geometry is written into the behavior of light over cosmic distances. Every time we observe distant galaxies and map their positions across the sky, we're indirectly doing a version of this triangle test. If space had strong curvature on the scale of the observable universe, the positions and angles between faraway galaxies would betray that fact. We might see distortions in the grid of galaxy positions, or subtle magnification effects, indicating that, overall, space isn't flat. So far, no such dramatic triangle distortion has been seen. The universe doesn't obviously twist or skew the grand patterns of galaxies in a way that screams non-Euclidean. That in itself is a clue. It suggests that if the universe is curved, the curvature is very gentle, spread over scales even larger than what we can survey so far. Within our observable patch, the rules of Euclidean geometry, triangles at 180 degrees and all, seem to hold quite well. But seem to is the operative phrase, because appearances in limited domains can be misleading. Just as sailors once assumed the ocean was endless and flat, until evidence of Earth's roundness emerged. We must be careful drawing global conclusions from a limited view. We learned that on Earth it took broad perspectives and long journeys to reveal curvature. For the cosmos, we must use a different kind of perspective, not by travelling ourselves, but by gathering light from distant reaches and piecing together the cosmic puzzle. Beyond triangles, there are other patterns and measures in this starlight that can give away the shape of space. Astronomers also use cosmic rulers and candles, celestial objects of known size or brightness, to measure the universe. These tools, along with the ticking of cosmic time, help turn faint starlight into a cosmic tape measure. In the astronomer's toolbox, light is not just something to look at, it's something to measure with. Imagine a star that suddenly detonates in a brilliant supernova, half a universe away. For a few weeks, it burns with a ferocity that rivals an entire galaxy. To the naked eye, it's just a tiny flicker in the night. But to those who understand it, that flicker carries a wealth of information. Certain types of supernovae have a secret. They all explode with almost the same intrinsic brightness, like bulbs of a known wattage scattered across the cosmos. When one of these standard candles ignites in a distant galaxy, we can compare how bright it looks to us against how bright we know it truly is. The difference tells us how far away it must be. A supernova that appears faint must be extremely distant, its light diluted over unimaginable expanses. A closer one blazes more brightly. In this way, these dying stars become cosmic yardsticks. Each flare of light is not only a dramatic event, but also a measurement, a luminous ruler etched into the fabric of space. This idea of standard candles was a turning point in astronomy. Over a century ago, astronomers discovered that some stars flicker and pulsate in a regular rhythm, and that their rhythm is tied to their true brightness. By watching their pulsations, one could infer how luminous they really were, and thus how far away they must be when their light finally reaches us. Those pulsing stars, like the famous Cepheid variables, became the first standard candles, allowing us to gauge the scale of our galaxy and beyond. Later, exploding stars, supernovae, took up the mantle, shining even brighter and visible across billions of light years. Each reliable beacon in the dark allows us to extend our tape measure further, step by step, galaxy by galaxy. When we measure the dimming of a supernova's light, we are essentially measuring the stretching of space itself. The light travels to us through the expanding universe, growing fainter, not just with distance, but with the expansion of space that spreads it thin. By the time it arrives, that light carries the imprint of how much the universe has expanded during its journey. Light can also act as a measuring stick in a more geometric way. Instead of brightness, think of size and angle. If we know an object's true size, say, a particular kind of galaxy or a distant cluster of galaxies, we can look at how large or small it appears from Earth and deduce its distance. This is similar to holding your thumb at arm's length against the moon. Knowing your thumb is a couple of centimeters wide and seeing it just cover the moon, you could in principle figure out how far away the moon is with a bit of geometry. Astronomers apply this idea on the grandest scales. They search for standard rulers in the universe, objects or patterns that have a known actual size. One remarkable example comes from the very early universe in the form of sound waves that left an imprint on matter. When the universe was young and hot, pressure waves, essentially sound, rippled through the plasma. When things cooled enough for atoms to form, those ripples froze in place, leaving a subtle pattern, a preferred separation between galaxies on a colossal scale, roughly 500 million light-years. Today, astronomers can observe the clustering of galaxies and detect this faint pattern. By comparing the known true scale of that ancient ripple to the angle it spans in the sky from our viewpoint, they can tell how the universe has expanded and whether space is curved. It's as if we found a giant ruler streaked across the heavens, and by reading the tick marks on that ruler, we learn about the shape and size of cosmic space. Not all cosmic rulers are so dramatic. Sometimes astronomers use more local benchmarks, the typical sizes of galaxies, or how light dims with distance, to gauge how volumes increase as we look farther out. If the universe's geometry were unusual, very distant objects might appear magnified or reduced in size. For example, in a positively curved universe, faraway objects could appear larger than expected, as if space were focusing their light. Conversely, in a negatively curved universe, distant objects would look smaller and more spread out. By and large, however, galaxies and their apparent sizes behave just as the flat model predicts, indicating that if curvature exists, it's subtle. And then there is time, the cosmic clocks that tick away in the darkness. The universe itself provides standard clocks that help us measure its expansion. Think again of that distant supernova. Not only does it shine with a known brightness, it also fades in a characteristic pattern over time. Imagine two identical fireworks exploding, one nearby and one very far away. The distant one doesn't just look dimmer, its sparkle seems to last longer, as if in slow motion. This isn't because it actually burns longer, but because the expansion of the universe stretches the light waves and the passage of time as we perceive it. A supernova that brightens and fades over a month in its own galaxy might take, say, 6 weeks to go through the same cycle as seen from Earth, if it's at a high redshift. The cadence of its flicker has been stretched out. By measuring this time dilation, how much the cosmic clock has slowed the flicker, astronomers can confirm the vast scales and expansion rates involved. Time itself becomes a measuring tool. The ticking of a pulsar, the orbital dance of binary stars, the rhythmic flashing of a distant quasar's light echo. Each of these can be compared across distances to see how the universe's expansion and gravity might be altering our perception of time's flow. In this way, cosmic timekeepers complement the cosmic yardsticks and candles in our quest to measure the universe. Using standard rulers, candles, and clocks, we start to build a cosmic distance ladder and a sense of the universe's geometry. We find that the rules of Euclidean geometry, the relationship between an object's size, its distance, and the angle it subtends, hold up extremely well on large scales, at least as far as we can see. The brightness of supernovae and the angles spanned by distant rulers all fit a pattern consistent with a space that is very nearly flat. If there is any curvature, it's so slight that these measures only hint at it, like a barely perceptible bend in an enormously long road. And yet, the measurements have to be interpreted within a framework, a cosmic model that ties together space and time. It's time to step back and see how all these pieces, distances, angles, times, curvature, come together in the grand scheme of cosmology. The Friedman-Robertson-Walker metric, the mathematical foundation for our expanding cosmos, awaits as our guide to the big picture. To truly understand the shape of the universe, we need a grander map, one that combines space and time into a single cosmic fabric. Imagine you have a blueprint of the cosmos, a kind of grid that stretches as the universe expands. This is what cosmologists call the metric of spacetime. The Friedman-Robertson-Walker (FRW) metric is one such blueprint. It's a mathematical description that tells us how distances in the universe grow or shrink with time, and how they might curve. It's as if the universe has an underlying pattern, a weave of space and time that can stretch like elastic and bend like a surface. Think of space at any given moment as a giant canvas. On this canvas, galaxies are sprinkled like paint. The FRW picture imagines that canvas expanding uniformly, every distance between galaxies increasing by the same factor over time. We call that factor the scale factor, usually denoted by a T, to remind us it changes with time. If a T doubles, it means every distance in the universe has doubled. Galaxies that were 1 million light-years apart become 2 million light-years apart. Those 10 million apart become 20 million. Importantly, the galaxies themselves aren't flying through space away from each other. Rather, space itself is stretching, carrying them along. Imagine raisins embedded in a rising loaf of bread. As the dough swells, every raisin grows farther from its neighbors without any raisin itself moving. Or picture dots drawn on the surface of a balloon. As the balloon inflates, every dot recedes from every other. In both cases, it's the medium, the dough or the balloon's rubber, that expands, dragging the objects with it, not the objects spontaneously flying apart. Now that balloon or loaf analogy brings up something crucial: the overall shape of space. The FRW metric allows for different shapes of the universe. Picture 3 scenarios. First, imagine our expanding cosmic canvas is perfectly flat, like an infinite sheet of graph paper being stretched. This is a flat universe. It goes on forever in every direction, and the rules of Euclidean geometry hold everywhere. Triangles sum to 180 degrees and so on, even as it expands. Second, imagine the canvas is like the surface of a sphere, in 3 dimensions instead of 2. This would be a closed universe with positive curvature. Like the balloon's surface, it's finite in size but has no boundary. If you travel far enough in one direction, you could end up back where you started, just as an ant crawling on a balloon loops around. This spherical universe still expands, but its geometry is curved back on itself. Third, imagine a saddle-shaped or Pringle chip canvas, an open universe with negative curvature. In that case, space is infinite, but curves in such a way that triangles have less than 180 degrees and parallel lines diverge. All 3 of these scenarios, flat, closed, open, are allowed in the FRW description. They differ by a simple choice of curvature: 0, positive, or negative. In each case, the expansion of space is described by the same kind of scale factor A of t, but the geometry affects what might ultimately happen. In a flat universe, the math suggests expansion could slow forever, but not quite stop, if only matter is pulling on it. In a closed universe, gravity is stronger. If there's enough matter, the expansion might eventually halt and reverse, ending in a big crunch, like a balloon that expands, then contracts. In an open universe, by contrast, there isn't enough gravity to ever stop expansion, so space would keep stretching forever. For decades, cosmologists tried to figure out which kind of universe we live in by measuring a number called the critical density. Einstein's general relativity links the density of mass energy in the universe to its curvature. There is a just right density, the critical density, that produces a flat cosmos. If the actual density is larger than that, space curves positively, spherical. If the density is smaller, space curves negatively, saddle-shaped. In the language of cosmology, we often use omega to denote this ratio of actual density to critical density. If omega equals 1, the universe is flat. If omega is greater than 1, space is positively curved. If omega is less than 1, it's negatively curved. Early in the 20th century, when Einstein and others first applied general relativity to the whole cosmos, They considered all these curvature options. Einstein himself initially favored a static, closed universe. He even introduced a cosmological constant, a kind of anti-gravity force, to counteract gravity and hold the universe in a steady state. This was before Hubble's discovery of cosmic expansion. Once Hubble found that galaxies are flying apart, the notion of a dynamic universe came to the forefront. The theoretical models of Friedman and others, which had predicted expanding or contracting universes, were suddenly vindicated. The universe was expanding, and its ultimate fate seemed to hinge on its density and curvature. The FRW metric doesn't just categorize space as flat, closed, or open. It weaves space together with time and tells how the cosmos evolves. Embedded in it are the Friedman equations, which come from inserting this metric into Einstein's field equations of gravity. These equations govern how the scale factor A of t changes with time, depending on what's in the universe. For example, a universe filled with only matter will gradually slow its expansion, since gravity pulls everything together. And if there's enough matter, omega greater than 1, that deceleration can eventually halt and reverse into a collapse. A low-density universe, omega less than 1, might expand forever, slowing but never stopping. The critical case, omega equals 1, is right on the border, slowing asymptotically but never quite halting if only matter is involved. This connection between density and fate was a cornerstone of mid-20th century cosmology. It meant that measuring the curvature was not just about geometry, it was about destiny. However, we now know there's more in the cosmic mix. In the late 1990s, astronomers discovered that the expansion is speeding up, driven by something we call dark energy. This mysterious pressure acts almost like anti-gravity, pushing space apart. Dark energy complicates the old picture of fate. Even a closed universe might expand indefinitely if dark energy dominates, and an open universe could in theory recollapse if dark energy were to behave strangely in the future. But in terms of geometry, dark energy contributes to the overall density too. So the rule still stands. The total omega, matter plus energy, determines the curvature. And all observations to date suggest that omega is very close to 1. In other words, the universe, as far as we can tell, is balanced on that flat knife edge. What does the FRW metric look like to an observer inside the universe? Imagine you are at a certain galaxy and you shine a beam of light toward a distant galaxy. That light travels through expanding space. The metric would tell you how to calculate the distance it covers and how the stretching of space affects it. For instance, the wavelength of that light will stretch by the same factor that space does. This explains the redshift we observe from faraway galaxies. It also tells you about volumes. How many galaxies you'd expect to find within a certain radius depends on the curvature. A closed universe has less volume in a given radius than flat space. An open universe has more. The metric is like a master equation for the cosmos's structure. One part of it encodes the curvature, and another part, through the scale factor, encodes the expansion. The beauty of the FRW description is its simplicity. It assumes the universe, on large scales, is homogeneous and isotropic, the same in all directions and places on average. That's why we can describe the whole vastness with just a few parameters. The scale factor A of t and the curvature choice plus parameters describing the contents like matter and energy, which determine how a t evolves. It's a bit like knowing the weave and pattern of a carpet without seeing every detail. You know the overall shape and design. With the FRW metric in hand, cosmologists have a foundation to interpret all those observations. Supernovae, ancient sound ripples, galaxy distributions, and more all must fit into a consistent picture governed by this expanding fabric. So far, our journey has focused on what we can see from within our cosmic patch, using light and space to infer the shape of things. But every journey has a horizon. To truly grasp the universe's shape, we also need to face the limits of our vision. The cosmos itself has horizons that define what's observable and what's forever beyond our reach. It's time to turn our attention to those horizons and understand what observable universe really means, and why even a locally flat space doesn't guarantee that the entire universe, beyond our sight, shares the same shape. No matter how powerful our telescopes become, there is a fundamental limit to how far we can see. The universe has horizons, boundaries not of solid walls, but of time and light. It's a bit like standing on a shore, looking out at the ocean. There's a line beyond which you cannot discern anything, not because the ocean ends, but because of the curvature of the earth and the limits of your sight. In cosmology, one horizon is set not by the curvature of space, but by the finiteness of time and the speed of light. Since the universe has a beginning and light travels at a fixed speed, there is a maximum distance beyond which light has not had time to reach us yet. This is the cosmic particle horizon, the edge of the observable universe. The particle horizon can be thought of as the distance light could travel from the Big Bang until now, about 13.8 billion years of travel time. However, because space has been expanding all the while, the current distance to the most distant things we can see is much larger than 13.8 billion light-years, roughly on the order of 46 billion light-years. What lies at that observational edge? The afterglow of the Big Bang, the cosmic microwave background, is essentially a photograph of the particle horizon as it was about 380,000 years after the Big Bang. Any region of space beyond that had not yet sent its light or heat to us by that time. So we see a foggy wall, the farthest surface of past visibility. We cannot see earlier than that with light, because before that epoch, the universe was an opaque plasma. In effect, we're looking at a baby picture of the universe, and anything beyond that point is outside our observable realm for now. Another kind of horizon concerns the future, the event horizon. If the universe's expansion continues to accelerate as it is today, thanks to dark energy, there will be regions of space that, although perhaps visible to us now, will eventually slip beyond our reach. An event horizon is a boundary beyond which events now will never affect us in the future. Imagine a galaxy so distant that the space between us and it is expanding faster and faster. Eventually, any new light that galaxy emits will never make it to Earth, because the intervening space expands too quickly. In the far future, that galaxy's light will simply never arrive. In practical terms, beyond a certain distance, the accelerated expansion of space will outrun even the fastest signal. We could wait trillions of years and see nothing new from beyond that boundary. This cosmic event horizon is analogous to a point of no return, a limit beyond which information will never come in. There's also the concept of a Hubble horizon, or Hubble radius. This is defined by the scale at which the current recession velocity of cosmic expansion equals the speed of light. At present, this Hubble radius is about 14 billion light-years. It isn't an absolute boundary. Galaxies beyond that distance can still be observed if their light set out long ago, but it's a useful notion for understanding scales of causality. Regions within one Hubble radius of us are, in a sense, communicating with us today. Their light is reaching us now, whereas regions much beyond that are receding so fast that their present light will reach us only in the far future, or not at all. In an accelerating universe, the Hubble horizon may approach a fixed size, effectively marooning distant galaxies beyond a certain point. When cosmologists talk about the observable universe, they mean the spherical region centered on the observer, us, from which light has had time to arrive since the universe began. It's our cosmic horizon in the past. We estimate its radius to be about 46 billion light-years, not because the universe is only that big, but because that's as far as light has travelled in 13.8 billion years of cosmic history, given the expansion. Importantly, beyond this observable universe, there may be, and most likely is, more universe, perhaps much more. Like sailors in ancient times, we gaze to our horizon and wonder what lies beyond. It could be more of the same universe, stretching on, or it could be something radically different. But it's beyond our sight, at least for now. These horizons impose a fundamental limit on our knowledge. We can build ever better instruments, but we cannot receive information from beyond the particle horizon, not until enough time passes for light, or some other signal to get here. We are cosmic horizon watchers, limited to our own observable patch. This means that some questions, like exactly how large or what shape the entire universe is, might not be fully answerable with direct observation. The universe could be enormously larger than what we can see, and its global curvature could be something our measurements haven't captured, because our visible region is just a small sample. Horizons also underscore why local measurements aren't the whole story for global geometry. We have found that the observable universe is remarkably uniform and apparently flat, but that observation applies only to the region we can see. The global shape of the universe might not be fully revealed within our observable patch. The universe could be curved on a scale far larger than our horizon, or have a topology, like a wraparound structure, that we can't detect because we only see a finite piece. In other words, our local lack of curvature is a clue, but not a guarantee of global flatness. Why is it then that the observable universe looks so flat? Is it perfectly flat, or just a part of a much larger curved picture? As we gather our clues and contemplate horizons, we're led to the next chapter of our cosmic detective story. Local measurements have given us hints of near flatness. To truly answer whether the universe is flat, infinite, or curved in on itself, we'll need to combine those hints with theory and look back to the universe's first moments. The journey continues as we go beyond the horizons of observation into the realm of cosmic origins and ideas that might explain why space is shaped the way it is. Now our journey turns to the faint echoes of the universe's first light. Imagine the cosmos when it was only a few 100,000 years old, long before galaxies or stars had formed, when everything was an incandescent fog. In that early era, space was filled with a hot, dense glow, like the embers of a fire illuminating every direction. As the universe expanded and cooled, it left behind a gentle afterglow that still surrounds us today. This afterglow is the cosmic microwave background, a faint whisper of radiance filling the sky. Truly the oldest light we can observe, a baby picture of the cosmos itself. Discovered by accident as a persistent radio hiss in the 1960s, the cosmic microwave background, or CMB, is almost uniform wherever we look. Its temperature is an icy 2.7 degrees above absolute zero, remarkably even from one corner of the sky to another. To the first astronomers who measured it, the CMB seemed uncannily smooth, almost featureless. But with more sensitive instruments, scientists uncovered tiny variations, speckles of slightly warmer or cooler glow scattered across space. These subtle spots, only a few 10,000ths of a degree different from their surroundings, carry a cosmic imprint. They are the fingerprints of the infant universe, encoding how matter and energy were distributed long ago. To picture these variations, one might imagine looking at a vast, quiet ocean at dawn. At first glance, the surface looks perfectly calm, but up close, you notice gentle ripples and swells. Similarly, the CMB's faint mottled pattern reveals that the early universe was not perfectly uniform. It had slight ripples in density and temperature. Those ripples have tremendous significance. Over billions of years, they grew into the galaxies and clusters of galaxies we see around us. Yet before they formed stars, while they were still just tiny fluctuations in an ocean of light and plasma, they left their mark on this primordial light. The cosmic microwave background we observe today has traveled for 13.8 billion years to reach us. It began its journey when the universe was about 380,000 years old, when the hot fog of plasma finally cooled enough to become transparent. In that moment, called last scattering, light was set free. Photons could stream across space rather than being trapped by electrons. From that time onward, the universe was dark and transparent, so those photons from the cosmic dawn could fly unimpeded. They have been racing through expanding space ever since, growing fainter and stretched to longer wavelengths, fading into a cool microwave whisper. When we tune our radio telescopes between the stars, we can still catch that whisper everywhere we point, a uniform hum from the young universe. What makes this ancient light so valuable to cosmologists is what's imprinted in its delicate patchwork of hotter and cooler spots. This pattern is often likened to a giant fingerprint or a baby's first portrait of the cosmos. Just as you might study an old photograph for hints of a person's youth, scientists examine the CMB for clues to cosmic infancy. In the arrangement of those subtle temperature ripples, they find a wealth of information about the universe's composition and shape. Certain patterns in the CMB tell us how much dark matter and ordinary matter existed back then, and even hint at mysterious dark energy to come. And importantly, the overall size and distribution of the spots on this sky map hold the key to deciphering the geometry of space itself. Think of drawing a pattern on a balloon versus on a flat sheet of paper. If the balloon is inflated or deflated, the pattern's apparent size changes. In a similar way, the size of the hot and cold patches in the CMB, how wide they appear on our sky, depends on the shape and stretch of space the light travelled through. If the cosmos were curved like a sphere or shaped like a saddle, it would subtly alter how those primordial patterns appear to us now. A given ripple from the early universe would look smaller or larger depending on whether space is positively curved, negatively curved, or flat. Thus, the CMB isn't just a pretty mottled picture, it's a cosmic measurement tool. It carries in it a record of the universe's geometry on the grandest scale. Over the decades, increasingly precise satellites and telescopes have mapped the CMB's faint speckles with astonishing accuracy. From the COBE satellite in the early 1990s, which first confirmed there were variations at all, to the WMAP probe in the 2000s and the Planck Observatory in the 2010s, each generation refined our baby picture of the universe. The picture came into sharper focus, a rich tapestry of minute temperature differences, arranged in a specific pattern of larger and smaller clumps. It turned out that the spots weren't random blobs, but bore the imprint of primordial sound waves that once rippled through the hot plasma. This was a stunning realization. The early universe rang like a giant bell, and the CMB captured the echoes of that ringing. In those echoes lay the secrets of cosmic curvature. As we hold up this ancient image and squint at its details, we can start to discern what it's telling us about the cosmos. The uniformity of the CMB tells us our universe is very nearly the same everywhere on large scales, a clue that something like cosmic inflation stretched it smooth in its infancy. The presence of slight irregularities tells us there were tiny quantum fluctuations that inflation amplified, planting the seeds for galaxies. And the scale of those irregularities on the sky, the typical size of a hot or cold patch, speaks directly to the geometry. It's as if the universe provided a built-in ruler in this baby photo, one we can use to measure the curvature of space. Even without knowing the technical details yet, one can appreciate the wonder here. By studying nothing more than a faint glow in the sky, we are able to infer the shape of everything. The cosmic microwave background is a silent narrator, telling the story of how space might be flat, or curved outward, or curved inward, all through a subtle pattern in a sea of microwaves. It is incredible that a phenomenon so gentle, the whisper of ancient light, holds answers to a question as profound as the shape of the universe. It's a testament to human curiosity that we can extract cosmic truths from such a quiet signal. Within the young universe's hot plasma, sound waves really did roll across the primordial sea. The early cosmos was like a vast arena filled with a fluid of light and matter, so dense and hot that particles and radiation moved together. Gravity tried to draw matter into dense clumps, while pressure from intense radiation pushed back, setting off oscillations, in essence, sound. These pressure waves rippled outward through the plasma, compressing and rarefying regions in a regular rhythm. If one could have heard it, though no ears existed then, the infant universe would have been humming with a deep, resonant tone. Each ripple in that primordial ocean travelled outward until a momentous event froze it in place. That event was the same recombination we touched on earlier, when the universe cooled enough for electrons and protons to combine into neutral atoms, and the fog lifted. At that instant, the plasma turned transparent, and the sound waves effectively stopped propagating. The pattern of compressions and rarefactions became imprinted on the matter and light at that time. One particular ripple, the largest one that had time to grow before everything went quiet, left an especially prominent mark. It's as if the music of the cosmos suddenly paused, and the sound waves' positions at that final beat were recorded permanently in the cosmic microwave background. When scientists analyze the CMB's faint patchiness, they find that certain spot sizes are more common than others, reflecting those ancient oscillations. The most common size, the dominant note of this primordial sound, corresponds to that largest ripple which had just enough time to compress once fully by the era of recombination. On the sky, this translates to hot and cold spots that are about 1 degree across. To visualize 1 degree, it's roughly twice the width of the full moon. Indeed, if you look at the all-sky map of the CMB, you will notice a characteristic granularity at about that scale. This is the imprint of the fundamental acoustic wave from the early universe. In technical terms, cosmologists see this as a peak in the CMB's angular power spectrum, a graph of how much fluctuation power exists at different angular scales. That first peak is the strongest, indicating that many patches about 1 degree across share similar temperature deviations. Additional, smaller peaks follow, corresponding to the overtones of the primordial sound at smaller scales. But it's the location of that first peak that is most revealing for the shape of space. The angle it subtends on the sky acts as a cosmic measuring stick. Since we know the actual physical size of that sound horizon at recombination, any major curvature of space would make its apparent angular size wrong, either magnified or shrunken relative to the flat universe expectation. Imagine shining a flashlight on a wall through different funhouse lenses. One lens might make the pattern look bigger, another smaller. In the cosmos, curvature plays the role of that lens. In a universe with positive curvature, closed like a sphere, light travelling through space converges, making distant patterns appear magnified on the sky. Those 1 degree spots from the CMB would look broader in a strongly curved, closed universe. Conversely, in a universe with negative curvature, open like a saddle, light rays diverge and distant features appear reduced in size, meaning that same primordial ripple would show up as smaller than a degree. By contrast, a flat universe is like a perfectly clear lens. The sound horizon's image on the sky retains its true scale, around 1 degree across. The cosmic microwave background data showed exactly that undistorted size. When the first high-precision measurements of the CMB's acoustic peaks were made around the turn of the 21st century, the results were striking. The primary peak fell exactly where the flat universe model had predicted it would. In other words, the characteristic hot and cold spot size matched a spatially flat geometry. Balloon-borne experiments like Boomerang and Maxima, and later the WMAP satellite, confirmed this finding. Our universe's largest acoustic ripple appears on the sky at about 1 degree, indicating that on cosmic scales, space is flat. This evidence was a watershed moment, offering empirical confirmation to the idea that we live in a geometrically flat cosmos. As observations improved, additional acoustic peaks were resolved in the CMB's power spectrum. Each peak added to the story, confirming further details of the early universe. The relative heights of these peaks told scientists about the cosmic ingredients, like the amounts of normal matter and dark matter. This agreement between prediction and measurement gave cosmologists great confidence in the standard model of cosmology. At the cornerstone of this model was the finding that the spatial curvature of the universe is either zero or extremely close to zero. The precision measurements by experiments such as the Planck satellite pinned down any deviation from flatness to only a tiny fraction. In essence, space, as far as we can observe, behaves just as Euclid would have expected. Triangles drawn across the cosmos have internal angles summing to 180 degrees, and parallel lines remain parallel on the grandest scales. Yet the story of those primordial ripples doesn't end with the microwave background. After recombination, the sound waves stopped moving in the plasma, but the matter, especially the dark matter, kept feeling the effects of those initial pushes and pulls. The largest ripple, in particular, left an imprint not just in the CMB's glow, but in the very distribution of galaxies that would form over billions of years. It's as though the sound wave, having left its mark on the light, also seeded a subtle preference in how matter clustered. In the next part of our journey, we follow this standard ruler beyond the CMB. We look for its tracks in the arrangement of galaxies and cosmic structures long after the primordial sea had calmed. Long after the primordial sound waves faded, their memory lived on in the distribution of galaxies. Imagine tossing a pebble into a calm pond. Ripples spread out, and if the water suddenly froze, it would preserve a faint ring pattern on the surface. In much the same way, the Big Bang's hot plasma sent out ripples. When the plasma cooled at recombination, the largest of those waves, the sound horizon, became imprinted on matter. Over billions of years, as dark matter coalesced into galaxies, that ancient ripple scale persisted as a subtle preference in their spacing. Galaxies, it turns out, are more likely to be separated by an enormous distance, about 500 million light-years, than by other distances. This is the enduring imprint of baryon acoustic oscillations, a relic of the universe's youth. This preferred galactic separation is extremely subtle. Individual galaxies don't line up in obvious spherical shells or patterns to the eye. Rather, it emerges statistically when one surveys millions of galaxies and measures how many pairs are found at each separation. In those vast catalogues, a faint bump appears at around that magic distance. That bump is the hallmark of the baryon acoustic oscillation BAO scale, essentially a standard ruler imprinted across the cosmos. The size of this ruler is set by the maximum distance a sound wave travelled in the primordial plasma before freezing out, which we know from the physics of the early universe. In co-moving terms, accounting for the expansion of space, it spans roughly 150 million parsecs, or around 490 million light-years today. Detecting this cosmic ruler was no small feat. It wasn't until the early 21st century that astronomers had surveys large and detailed enough to reveal the BAO feature. In 2005, two independent teams analyzing the distances between hundreds of thousands of galaxies found the first clear signs of the BAO bump. It was a thrilling confirmation that the patterns seen in the CMB were echoed in the arrangement of galaxies, billions of years later and billions of light-years across. Here was a direct link between the universe's baby picture and its grown-up structure, evidence that the tiny ripples of the early cosmos guided the formation of cosmic architecture on the grandest scales. The BAO standard ruler provides a powerful tool for cosmology. Because we know the ruler's true length, we can use it to measure the universe's expansion at different epochs. It's rather like having markings on a cosmic yardstick. By seeing how large the BAO scale appears at various distances, or redshifts, scientists can infer how much the universe has expanded in the meantime. In a universe of different geometries or expansion histories, the apparent size of the BAO pattern would shift. For instance, if the cosmos were curved, or if the expansion rate changed dramatically, the observed separation corresponding to 500 million light-years might look off, too small or too large compared to expectations. So far, measurements of the BAO scale across a range of distances have lined up beautifully with the flat, accelerating universe model that emerged from the CMB and supernova studies. By combining BAO data with other observations, cosmologists can further tighten the constraints on spatial curvature. The BAO results have consistently indicated that we live in a universe best described by flat geometry within current errors. They also offer an independent check on the expansion driven by dark energy, since the BAO standard ruler can trace how the expansion has accelerated over time. With these ripples frozen in galaxy maps, we now have a way to chart cosmic distances that echoes the testimony of the CMB. The shape of the universe isn't read from one source alone. Multiple lines of evidence reinforce the picture. And beyond the subtle clustering of galaxies, astronomers have other cosmic yardsticks and signals to consider. Exploding stars, the bending of light by gravity, even the ripples of spacetime itself. All of these phenomena can serve as tools to gauge the cosmos. As our journey continues, we turn to these diverse and dramatic measures to see what they reveal about the universe's size, scale, and curvature. Not all cosmic measurements come from subtle background ripples. Some arrive in brilliant flashes of light, or in the bending of light itself, or even in faint tremors in the fabric of space-time. These are the candles, lenses, and sirens of the cosmos, diverse tools that help astronomers gauge distance and geometry. One of the most storied tools is the Type 1a supernova. These are titanic stellar explosions, white dwarf stars that ignite in a thermonuclear blast, which shine with extraordinary brightness. Crucially, Type 1a supernovae reach nearly the same peak luminosity every time. That consistency allows astronomers to use them as standard candles, objects of known true brightness. By comparing how bright a Type Ia supernova appears from Earth to how bright it truly is, one can deduce its distance, much like judging how far away a lantern is by its faintness. In the late 1990s, two teams of astronomers set out to map the expansion of the universe by observing distant Type Ia supernovae. They painstakingly gathered data on these exploding stars and measured their brightness across vast distances. To their surprise, the far-off supernovae appeared dimmer than expected. That indicated they were farther away than the current models predicted. The universe's expansion wasn't slowing down as most had assumed. It was actually speeding up. This discovery of accelerating expansion, attributed to a mysterious dark energy, revolutionized cosmology. The universe's energy budget now clearly required a new component to explain the observations. Matter, including dark matter, accounted for only about 30% of the density needed for a flat cosmos. The supernova evidence implied the remaining 70% was this dark energy, permeating space and driving the acceleration, thereby filling the gap and bringing the total density to essentially 100% of the critical value. In this way, the Type Ia supernova candles not only revealed the universe's acceleration, but also unveiled the missing energy that makes the cosmos geometrically flat. Light can also be used in another clever way to measure cosmic distances, not by its brightness, but by its bending. According to Einstein's general relativity, mass curves spacetime, and light travels along those curves. This means a massive object, like a galaxy or cluster of galaxies, can act as a gravitational lens, bending the light from objects behind it. Sometimes this lensing creates multiple images or smears background galaxies into arcs. The degree of bending depends on the geometry of space between the observer, the lens, and the background object. So if we understand the mass of the lens, we can use the amount of bending as a sort of cosmic ruler. Gravitational lensing provides several avenues for cosmology. In one scenario, a distant quasar, a bright galaxy nucleus, might be lensed by a foreground galaxy into two or more separate images. Each image's light takes a slightly different path through space-time to reach us, so variations in the quasar's brightness arrive at different times in each image. By measuring these time delays, essentially a race between light beams, and knowing the separation of the images, astronomers can infer the distances involved. This technique, called time delay cosmography, gives an independent measurement of the Hubble constant, the current expansion rate, and by extension, can inform curvature measurements. On a larger scale, entire clusters of galaxies serve as gravitational lenses. They bend and magnify the light of galaxies behind them, producing dramatic halos and arc-like images in the sky. By modeling these distortions, scientists can extract the distance ratios between the observer, the lens, and the background galaxy. In this way, massive clusters provide another way to measure cosmic distances, independently probing the geometry of space. Even more pervasive is weak gravitational lensing. As light from distant galaxies travels across the universe, the cumulative tug of intervening matter very slightly distorts their shapes. By statistically analyzing these tiny shears in the images of millions of background galaxies, cosmologists can map the distribution of dark matter and also gauge the geometry of space. The strength of lensing at different distances carries the imprint of how matter is distributed and how space expands, both of which are sensitive to whether the universe is flat or curved. Surveys like the Dark Energy Survey and the upcoming Euclid telescope devote enormous effort to measuring these subtle lensing patterns, all to further refine our understanding of the cosmic recipe and cosmic curvature. And then there are the standard sirens, a new kind of cosmic beacon, not of light, but of gravity itself. In 2017, scientists detected gravitational waves from a merging neutron star pair and simultaneously observed light from the collision. This was a watershed moment. From the gravitational wave signal alone, they could estimate the distance to this cataclysm, much like estimating distance from a sound's volume, once you know how loud the source is. By identifying the galaxy where the merger took place, they also obtained a redshift. With just this one standard siren event, they produced an independent measurement of the universe's expansion rate. As gravitational wave observatories improve and gather more events, especially those with light-based counterparts or identifiable host galaxies, we will accumulate a new trove of cosmic distance markers. Each such merger provides a direct measurement of distance from its gravitational signal and, with an identified redshift, a point on the cosmic expansion curve. With enough of them across different epochs, scientists can trace the expansion history in an entirely new way. These cosmic sirens are poised to test our cosmological models, including the spatial curvature of the universe, by providing an independent check on the distance-redshift relationship. Each of these methods, supernova candles, gravitational lenses, and gravitational wave sirens, approaches the cosmic distance problem from a different angle, and each reinforces the others. Supernovae map the expansion using the brightness of exploding stars. Lenses exploit the universe's gravitational optics to measure distances. Sirens carry information in ripples of spacetime. Together with the CMB and BAO, these techniques form a powerful network of cross-checks on the cosmic distance scale. When all these distance indicators are combined, we can construct a cosmic distance redshift relation, essentially a map of how far away things are at each redshift. If space has any curvature, it would appear as a subtle distortion of this map, a mismatch between distances and redshifts compared to the flat universe prediction. So far, however, every measurement, from candles to lenses to sirens, has been consistent with a flat universe. Still, the map-making continues with ever greater precision, in case a small curvature might yet lurk beyond our current reach. With multiple tools now charting the heavens, we stand ready to read the cosmic map more precisely than ever. The next step is to examine that map itself, the relationship between redshift and distance that these varied observations have drawn, and see how the geometry of space manifests in it. By looking at the cosmos as a whole, as a sort of gigantic map with scale markers, we can use redshift as a compass to discern the curvature, or lack thereof, of the universe. Suppose for a moment that the universe, while vast and seemingly unbounded, is actually finite. That if you travelled far enough in one direction, you'd eventually loop around and return to your starting point. This exotic idea doesn't necessarily contradict our measurements of flat geometry. Space could be flat yet multi-connected, like a vast three-dimensional loop. A classic analogy is the old video game Asteroids, where a spaceship leaving one edge of the screen reappears on the opposite edge. In a similar way, the real universe might effectively wrap around on itself. If it does, there's a chance we could catch it in the act, by seeing the same distant regions of space in more than one direction on the sky. The best place to look for such repetitions is the cosmic microwave background. The CMB covers the entire sky and comes from a fixed distance, the surface of last scattering, making it a giant canvas that could reveal a multi-connected topology. If the universe is smaller than that shell, meaning the observable universe wraps around itself, then the pattern of hot and cold spots on one side of the sky might align with the pattern on the opposite side, because they're actually the same region of space seen twice. Specifically, researchers have searched for matched circles in the CMB, pairs of circles with identical temperature fluctuations that would indicate the same physical location being observed from two directions. Beginning with the WMAP satellite in the early 2000s and continuing with the Planck mission, scientists carried out extensive searches for these matched circles. The technique involves scanning the CMB maps for circles or nearly circular patterns of a given angular size and checking every possible pair of orientations to see if the temperature variations along one circle match those along another circle elsewhere. It's a bit like taking two jigsaw puzzle pieces from opposite sides of the picture and seeing if they fit perfectly. So far, the result has been no convincing matches. The absence of identified matched circles suggests that if the universe is finite and wraps around, its fundamental scale is larger than the sphere we can observe. In other words, space might still be closed in on itself, but on a scale beyond our cosmic horizon, perhaps far beyond. One intriguing proposal in the early WMAP days was that a specific multi-connected shape, a dodecahedral space, think of a 12-sided die in Dungeons & Dragons, could explain a slight lack of large-scale variation in the CMB. This Poincare dodecahedron model implied a universe just a bit smaller than our observable volume, which could produce weak matching signatures. For a time, some saw hints of unusual correlations in the WMAP data consistent with that shape. However, subsequent analyses and the higher resolution Planck maps did not find strong evidence supporting such a specific topology. The low-power anomaly on large scales remains. The CMB does show slightly less variation on the biggest angular scales than the simplest theory predicts, but most scientists attribute this to cosmic variance or just statistical fluke, rather than a definite sign of a wrapped-around cosmos. In cosmology, a null result can be just as significant as a positive one. The lack of observed pattern repetitions has allowed researchers to place lower bounds on the size of a finite universe. Those bounds indicate that if the universe is finite, it must extend well beyond the radius of our observable horizon. Often estimates say at least several times larger. In effect, we've pushed the possibility of a detectable wraparound universe out of our current view. The universe could still be finite in some grand way, perhaps shaped like a torus or a complex polyhedron. But if so, it's so vast that the light hasn't had time to circumnavigate it within the age of the universe. While no circles in the sky have been found, this investigation highlights how carefully scientists are checking even the subtlest aspects of the CMB for clues. The quest to determine the shape and size of the universe combines both the precise, statistical analysis of patterns and the whimsical, imaginative models of space. So far, the simplest assumption, a flat, possibly infinite expanse, has survived all such tests. But the door isn't completely closed. It's just pushed out to scales far beyond our cosmic horizon. Having searched for grand cosmic patterns and largely drawn a blank, cosmologists turn back to scrutinize smaller anomalies and subtle features in the data. In the next chapter, we will delve into those delicate imprints, the little tilts, variances, and curious alignments that remind us how carefully we must read the cosmic message written in light. No cosmic measurement is perfectly neat and tidy. There are always statistical uncertainties and one-of-a-kind oddities that must be carefully considered. In the case of the cosmic microwave background and other cosmological observations, scientists have catalogued a few curious features, subtle patterns in the noise, as it were, that provoke discussion. They don't overthrow the standard picture, but they remind us of the limits of inference when dealing with a sample size of one universe. One fundamental limitation is known as cosmic variance. Because we have only one sky to observe, the largest scales, those with the fewest samples across the sky, are subject to huge inherent uncertainties. For example, the CMB's quadrupole, essentially the amount of variation between one half of the sky and the other, is just one data point from our single universe. Even if the true underlying theory predicts a certain average quadrupole strength, our particular universe's realization of it might be higher or lower just by chance. Indeed, the observed quadrupole in our sky is a bit lower than the most likely value expected from the best fit model. Is that a problem? Probably not. Given cosmic variance, it's not implausible to have a low quadrupole. our universe could just be slightly unlucky in that draw. With only one universe to measure, rare statistical flukes can and will happen occasionally. Beyond overall amplitudes, there are other small anomalies. One is often called the axis of evil, an observed alignment of the CMB's largest modes. The quadrupole and octupole, the patterns dividing the sky into 4 and 8 patches, respectively, in our sky, are not oriented randomly with respect to each other. Instead, they seem to align along a common axis across the sky. This was not expected under basic isotropy assumptions. Some have wondered if it hints at unknown effects beyond our observable universe, while others suspect it's simply a statistical quirk. As data improved with WMAP and Planck, the alignment persisted, but its significance is debated. Roughly a few % chance of occurring, which is low, but not extraordinarily so. It's enough to spark interest, yet not enough to claim a discovery of new physics. Then there is the CMB cold spot. Discovered in WMAP maps and confirmed by Planck, it's a region of the sky about 5 to 10 degrees across that is noticeably cooler by around 70 microkelvins than the surrounding areas. Statistically, one would expect some patches that cold in the entire sky, but the cold spot is somewhat larger and deeper than average expectations. What could it be? Explanations range from a supervoid, an enormous underdense region along that line of sight that could cool the CMB via the Sachs-Wolf effect, to more speculative ideas like a remnant imprint of a collision with another universe. Most cosmologists lean toward a more prosaic explanation. It could well be another case of our universe rolling an unlikely, but not impossible, outcome on the dice. The jury is still out, but so far no compelling evidence has arisen that the cold spot is anything beyond an interesting statistical fluke or a feature of foreground structures. Another subtle pattern is the slight hemispherical asymmetry in the CMB. If you divide the sky into 2 halves, one half shows marginally higher variance, more overall fluctuation, than the other. This hemispheric imbalance again violates the ideal of perfect isotropy. It's as if the universe had a marginal preference for one side. Like the other anomalies, it's uncertain whether this is just random chance, or hints at something like an early universe asymmetry. Current thinking is cautious. While intriguing, these asymmetries have not pointed clearly to new physics, and they might diminish or change character with different data processing choices, hinting that they could be partially due to astrophysical foregrounds or measurement artifacts. One key lesson from these oddities is the danger of a posteriori analysis, finding patterns after the fact. If one sifts through enough data, some combination of points will always look special. That's why scientists use statistical penalties for look elsewhere effects and remain conservative about claiming new physics based on low probability features that were not predicted ahead of time. So far, none of the strange alignments or cold spots has risen to the level of demanding a revision of the standard cosmological model. They live in the grey area between noise and signal, tantalizing but inconclusive. Still, these subtle patterns are a valuable reminder. They remind us that even in this age of precision cosmology, our conclusions rest on probabilistic foundations. We must always account for the possibility that an apparent surprise is just randomness playing tricks. At the same time, it's worth keeping an eye on these curiosities. If a pattern were to grow stronger with new data, or if multiple independent anomalies pointed toward the same effect, we would have cause to reconsider our assumptions. Science often advances by explaining the exceptions. For now, though, the exceptions in the CMB and large-scale structure seem well within the bounds of chance and standard physics. Our overall cosmic story, a nearly flat universe seeded by inflation, structured by known physics, remains intact and robust, with these anomalies adding a touch of intrigue at the margins. After surveying these minute irregularities, we find that our fundamental conclusions remain unshaken. The universe's shape still appears to be flat on the largest visible scales, and the cosmological principle of isotropy holds to a remarkable degree, save for these tiny wrinkles. In the grand tapestry, the threads still weave into a consistent picture. As we prepare to summarize the state of knowledge, we keep in mind both the triumph of our model and the small mysteries that keep us searching deeper. In broad strokes, the cosmos we've uncovered is one that is spatially flat, or so nearly flat that any curvature is imperceptible. All the major threads of evidence converge on this conclusion. The CMB's acoustic peaks land exactly where a flat universe would place them. Galaxy surveys, mapping baryon acoustic oscillations, see patterns that align with flat space distances. Supernovae and other distance indicators all fit comfortably into the flat model when we include the known ingredients of matter and dark energy. Quantitatively, when cosmologists express the curvature in terms of the density parameter omega k, the best estimates put it at on the order of 0.000 plus or minus 0.002, consistent with zero within tiny uncertainties. We cannot say with absolute certainty that the universe is exactly flat. There's always the possibility of a tiny curvature beyond our current sensitivity. However, if such curvature exists, it corresponds to a radius so immense that space within our observable cosmos would still appear flat. In other words, any bending of space is too subtle to detect with current data. This reinforces the conclusion that our visible universe is effectively Euclidean. This triumph of a near-flat universe is accompanied by a big asterisk. It assumes the correctness of the current cosmological model, lambda CDM. Flat, in this context, means that given our best understanding of the contents of the universe, roughly 5% ordinary matter, 25% dark matter, and 70% dark energy, the geometry comes out flat. The caveat is that if any of those ingredients is not what we think, or if new physics is lurking, our inference of flatness might need revision. For instance, we assume dark energy behaves as a cosmological constant. If it actually varies with time, or has a more complex behavior, it could mimic a slight curvature in certain datasets. At present, though, no alternative model fits the myriad observations better than flat lambda CDM. It's worth noting that the flatness of the universe is often seen as support for the theory of inflation, which naturally drives space toward flatness. In a sense, inflation predicted what we observe, space so flat that it's hard to measure any deviation. Some scientists take this further, suggesting that inflation might have made the universe far larger than what we can see, meaning any curvature could be outside our observable horizon entirely. If that's the case, our measurements of zero curvature are no surprise at all, and any tiny residual curvature we might someday detect would be a remnant of imperfect inflation, or some feature beyond the simplest models. Are there any remaining hints that challenge perfect flatness? One mild tension arose in recent years. Analyses of the Planck satellite's CMB data, when taken in isolation, showed a slight preference for a closed universe, a positive curvature. If taken at face value, Planck's high-precision maps yielded a curvature parameter, omega k, of about minus 0.04, which would imply the universe is very slightly curved in on itself. This result was puzzling, because it disagreed with other evidence like BAO and supernovae, and even with Planck's own lensing data. Most experts suspect this was a statistical fluctuation, or an unresolved systematic in the CMB data. This is essentially a 1% statistical blip in the data, not a genuine feature. Indeed, when all data are combined, the hint of curvature vanishes, snapping back to omega k, approximately 0.00. Still, This episode serves as a reminder that we must handle even precise data with care. A chance fluctuation can momentarily point us in a strange direction, but cross-checks and new data inevitably bring the picture into sharper focus. Aside from curvature, the current cosmological model has a few other wrinkles, notably the ongoing Hubble tension, where local measurements of the universe's expansion rate, the Hubble constant, are somewhat higher than the value inferred from the CMB and other early universe data. This discrepancy has prompted speculation about new physics, ranging from exotic particles to early universe phenomena that might adjust the expansion history. Importantly, none of the leading explanations for the Hubble tension involve spatial curvature. It appears to be an orthogonal issue. We mention it as a caveat that flat lambda CDM is not a perfect story. It fits an enormous amount of data extremely well, but not every piece of data. Whether the Hubble tension is a sign of new physics or just an unknown error, it doesn't undermine the conclusion of flat geometry. So, with all major lines of evidence considered, our best fit description of the universe today is a flat, expanding spacetime dominated by dark energy in the form of a cosmological constant and dark matter, with ordinary matter as the minor ingredient. It's a universe that will likely keep expanding indefinitely, given that in flat or open geometries with a cosmological constant, there's no turnaround. Only in a sufficiently curved, matter-dominated universe would gravity someday halt and reverse the expansion. The near flatness we observe, combined with an accelerating expansion, paints a picture of a cosmos that is infinite, or at least enormously extended in space, and headed toward a vast and cold future. There are, of course, profound mysteries still wrapped up in that tidy description. We still don't know what dark matter is, nor the true nature of dark energy. We don't know why the universe's curvature is so close to zero, whether it's exactly zero for deeper fundamental reasons, or just an outcome of initial conditions smoothed by inflation. Our measurements keep tightening the margins on curvature, and so far, they continue to point to flatness. Future missions and surveys will further improve the precision, testing whether perhaps a minute curvature might reveal itself with better data, or whether the flatness is absolute to the limits of measurement. At this point in our cosmic voyage, it's fair to say the shape of the universe, at least within the observable horizon, is one of the things we've come to understand quite well. It is flat to the best of our measuring ability. This knowledge is a triumph of modern cosmology, a testament to the interplay of theory and observation. Yet, like any good scientific conclusion, it remains open to revision by future evidence. As we conclude this part of our journey, we stand under a sky mapped in detail, confident that we live in a universe without notable curvature, but aware that this achievement still leaves some big questions. Determining flatness is not an end, but a beginning, a foundation on which to ask even deeper questions about how our universe came to be and what its ultimate fate will be. The cosmos reveals an uncanny balance. By all we can measure, space itself spreads out in a nearly perfect flat expanse. This flatness is subtle. You wouldn't notice it looking around, but it's coded in the gentle geometry that guides the paths of light and the dance of galaxies. For astronomers, seeing such a flat universe is at once comforting and deeply perplexing. Like a coin spinning on its edge without ever toppling, the universe seems to hold an almost impossible poise. If the universe had been even slightly more curved in shape long ago, it would not look this way now. Over billions of years, any initial curvature would have grown dramatically. A universe just a bit too dense would have curved inward on itself like a sphere, its own gravity dragging it closed. Eventually, the expansion might have slowed and even reversed. A universe just a bit too thin, not dense enough, would have curved outward like a saddle and expanded so fast and freely that galaxies might never have formed. But our universe has expanded for eons without either collapsing under its own weight or flying apart beyond structure. It rides the razor's edge between too much gravity and too little, between closed and open, as if finely tuned to perfection. This delicate balance is what cosmologists whisper about as the flatness problem. Observations of the cosmic microwave background and distant galaxies all whisper the same story. The spatial fabric of the cosmos is flat to within a hair's breadth of absolute perfection. To be so flat now, after nearly 14 billion years of cosmic evolution, the universe must have started out unbelievably close to exactly balanced. If there was even a tiny deviation in the beginning, cosmic evolution would have amplified it enormously. Calculations show that to stay this near flat today, the universe's initial density had to be set with astonishing precision, on the order of 1 part in a million, trillion, trillion, trillion. Imagine aiming for a target and hitting within a margin of error smaller than a single grain of sand out of an entire beach. That is the level of cosmic fine-tuning we're talking about. For many cosmologists, such precision in the initial conditions cried out for an explanation beyond chance. Such a precise initial setup feels almost too perfect to attribute to mere chance. It's as if the universe knew from the very start exactly how much matter and energy to have, like a recipe measured with cosmic precision spoons. Without some special reason, this kind of immaculate balance is puzzling. In the late 20th century, scientists found themselves asking, why should the Big Bang have been so extraordinarily fine-tuned for flatness? Was it a cosmic coincidence? Or was there some hidden process that naturally put the universe on this knife edge of balance? The flatness problem lingered like a soft, nagging whisper in cosmologists' minds. A hint that something important was missing from the classical Big Bang story. They suspected that nature might have had a trick up its sleeve in those first instants, an extraordinary process that could elegantly set the cosmos on its flat course. One revolutionary idea emerged, a bold proposal for that silent dawn. What if space itself underwent an incredible growth spurt in its first tiny fraction of a second? In the early 1980s, cosmologists began to suspect that the universe, when it was less than a trillionth of a second old, might have suddenly inflated, swelling enormously in size in an almost unimaginably brief moment. Picture the fabric of space stretching rapidly outward, like a balloon inflating at a fantastic speed. All the vast expanse we now see, billions of light years across, could have been blown up from a volume far smaller than a pinhead. This idea was aptly named cosmic inflation, and it promised to smooth and flatten the young universe in one grand cosmic breath. During this extraordinary burst of expansion, any initial wrinkles or irregularities in space would have been stretched flat. Regions that were once tiny and curved would be pulled so far apart that they'd appear essentially flat, just as a small patch on a curved balloon looks flat when you zoom in. Inflation would push the geometry of the universe toward perfect flatness, like a master glassblower heating and blowing a molten sphere into a vast, thin sheet. At the same time, any clumps of matter or hotspots would be ironed out, leaving the universe extremely smooth and uniform in all directions. This offered a compelling answer to not only the flatness puzzle, but another cosmic mystery, the horizon problem. Why the universe looks so uniform, with distant corners sharing the same temperature and properties, even though they are too far apart to have ever exchanged light or information under normal expansion. In the inflation picture, those far-flung corners of the cosmos were once snuggled close together, part of the same cozy patch of space. Before the inflationary surge, the entire region that would become our observable universe was tiny, perhaps small enough that temperature and density had time to even out, as if the universe started in a warm, tiny room where everything could mix and settle into equilibrium. Then, in a flash, the walls of that room blew outward at tremendous speed, expanding 1,000,000,000,000,000,000-fold or more. The tiny, smooth patch was stretched into the vast cosmos we see today. Distant galaxies, now separated by tens of billions of light years, were originally mere millimeters apart, or closer, before inflation flung them to the far reaches. This dramatic stretching meant that when light finally could travel freely much later, every direction it went looked much the same because it all came from that single, well-mixed patch. Crucially, inflation wasn't just a fast expansion. It was a very special kind of expansion. It was driven by a peculiar form of energy that permeated space itself, causing a repulsive gravity effect. In general relativity, gravity can push as well as pull if the conditions are exotic enough. During inflation, space filled with what you might imagine as a high-energy field, often dubbed the inflaton field, that had a built-in tendency to make space accelerate outward. For a fleeting instant, this inflating energy dominated everything, overpowering the usual gravity that would normally pull matter together. Space didn't just expand, it blew up exponentially, doubling in scale again and again at a mind-boggling rate. To get a sense of the scale, think of an initial space so small that it's invisible to any microscope. Then imagine it doubling in size, and doubling again and again, over and over, very quickly. Even if you double something only a few dozen times, it grows from microscopic to astronomical. If the universe doubled in size about 60 times, a number often cited by scientists studying inflation, it would have expanded by a factor of about 10 to the 26th power. That's 1 with 26 zeros. An expansion factor so huge it defies easy visualization. In physical terms, that could be like blowing up a region smaller than an atom to something the size of a galaxy, all within a fraction of a second. More moderate illustrations say a patch perhaps 10 to the negative 30th meters across might have ballooned to almost a meter across in an eye blink. However you picture it, the message is the same. Inflation magnified the early universe by an astronomically large factor in almost no time. Such a rapid and tremendous stretching event would radically reshape the cosmos. Tiny curves in space would straighten out. Imagine drawing a small curve on a deflated balloon, then inflate it enormously. The curve spreads and straightens over the expanded surface. Similarly, any slight curvature the universe may have had was diluted away by inflation's blow-up. Space, at large scales, would now be extremely flat, just as observed. And any disparate, uneven features, a dense clump here, an empty void there, would be smoothed to near uniformity. Inflation essentially pressed the cosmic reset button on irregularities, leaving behind an almost pristine canvas. This idea was captivating, because it seemed to answer fundamental questions so neatly. What once looked like incredible coincidences, the fine-tuned flatness and the uniform sky, now could be natural outcomes of a simple cosmic growth spurt. For the first time, it seemed one grand mechanism could resolve multiple cosmic mysteries at once. If inflation happened, the flatness problem might not be a problem at all. The universe would flatten itself out. No fine precision at birth required. Likewise, the distant reaches of the universe would share the same properties, because they all came from the same small, harmonious beginning. Inflation turned the early universe into a kind of pristine paradise, smooth, flat, and ready for the next chapters of cosmic history to unfold. It neatly set the stage for the formation of stars, galaxies, and all the complexity to come. Yet inflation was a radical hypothesis. It described a period far beyond any direct experiment, a kind of new physics, operating at unimaginable energies. It pushed physics into realms we could only theorize about. Some scientists were initially skeptical of such an extraordinary proposal. Still, it made concrete predictions that could be tested, particularly about tiny imperfections in that otherwise smooth cosmos. Inflation wasn't a perfectly uniform blow-up. Quantum theory tells us there would be tiny random fluctuations even in the inflating field. And inflation, by stretching everything, would magnify those microscopic fluctuations into macroscopic ripples, subtle imprints that would later seed galaxies and other structures. These seeds, born from quantum randomness, would be the smoking gun evidence that inflation truly occurred. The stage is set to understand how such minute quantum whispers during inflation grew into the grand structures we see in the universe today. In the eerie silence of the inflating universe, something profound was happening on the tiniest scales. Inflation may have smoothed the cosmos to near perfection, but it could not make everything exactly uniform. The reason lies in the jittery nature of the quantum world. Even in what seems like empty space, quantum physics tells us there is never complete stillness. Fields and particles experience tiny random fluctuations, popping in and out of existence for the briefest moments. Normally, such quantum jitters are impossibly small, far too tiny to have any cosmic effect. But inflation acted like a magic magnifying glass. Imagine the very young universe as an almost featureless, dark expanse under the grip of inflation, cold and nearly empty, yet not perfectly still. Little flickers of energy flit about at subatomic scales. These are the quantum fluctuations, random little deviations in the density of that inflaton field and in spacetime. Under normal circumstances, they'd cancel out or remain confined to the microscopic realm. But as space expanded so violently fast, these tiny fluctuations were pulled apart, dragged to macroscopic separations. A fluctuation that originally spanned, say, a billionth of a trillionth of a centimetre could suddenly stretch to span light years across. Once inflation ended, these stretched out irregularities became imprinted differences from place to place. One region might be ever so slightly denser than another, one spot a touch warmer, another a touch cooler. The differences were incredibly tiny, just parts in 100,000. But they were real, and they were there, woven into the otherwise smooth canvas of the young universe. These subtle imprints were the primordial seeds of structure. Where there was a tiny bit more density, gravity would later tug a little harder, gradually pulling more matter in. Where there was a bit less, matter would flow away to regions of higher gravity. Over millions and then billions of years, these slight head starts, essentially random speckles laid down by quantum chance, grew into the vast cosmic web of galaxies and clusters we see today. It's astonishing to realize that every galaxy, every cluster of galaxies, might owe its existence to a quantum whisper during inflation, in the afterglow of the Big Bang, the cosmic microwave background. We can still see a faint pattern, like a gentle mottling, which corresponds to those seeds. Satellite missions and telescopes have mapped these tiny temperature variations across the sky, finding just the kind of nearly scale-invariant, random speckles that inflation predicted. The universe's largest structures today are the amplified descendants of the smallest possible fluctuations, evidence of inflation's handiwork written across the heavens. The term quantum frost beautifully evokes the image. Think of an early winter morning, a thin layer of frost delicately coating a pane of glass with intricate patterns. In the inflationary epoch, the vacuum of space was in a near-frozen state, chilled by the rapid expansion and dominated by the inflaton field's cold presence. Across that vacuum, quantum fluctuations etched subtle patterns, much like frost crystals spreading in random, beautiful swirls. When inflation ended, it's as if the window pane suddenly expanded to the size of a continent, preserving those frosty patterns as broad strokes across space. What began as imperceptible quantum quirks became the blueprint for stars and galaxies. As inflation's furious growth subsided, it handed the baton of cosmic evolution to these primordial fluctuations. The universe was still dark, and hot radiation had yet to escape, but the pattern was set. In time, when the cosmos cooled enough for light to travel freely, these density variations revealed themselves in the light. Slightly warmer and cooler spots in the cosmic microwave background, first detected as faint patches, a few parts in 100,000, brighter or dimmer. The discovery of those patches decades ago was a milestone. It confirmed that the early universe wasn't perfectly smooth. It had just the right kind of tiny irregularities for gravity to later sculpt into galaxies. Inflation offered an elegant explanation for the origin of these irregularities. They were quantum seeds, laid down during the fleeting frost of the inflationary epoch. It's a mind-bending connection between the smallest and largest scales, the subatomic randomness of quantum physics blown up to seed the grand architecture of the cosmos. Without inflation, it's hard to imagine how the Big Bang alone could produce exactly the kind of initial lumpiness needed for galaxies to form. Too much lumpiness would have been chaos, too little, and nothing would coalesce. Inflation naturally gives just a tiny, random nudge everywhere, which turned out to be just enough. The result is a cosmos that is remarkably uniform on the whole, yet not utterly featureless. It contains the perfect imperfections. These are the slight deviations that gravity could work on to build everything interesting in the universe. Thus, cosmic inflation left a twofold legacy: a nearly flat, smooth cosmos, and a faint fingerprint of quantum noise that would later become all the structure we see. In a very real sense, we are here, living beings on a planet around a star in a galaxy, because of those microscopic fluctuations during inflation. They are the original makers of cosmic structure, whispering the promise of galaxies into the fabric of space when the universe was less than a blink old. Now that we've traced how inflation planted these seeds, we can delve deeper into exactly how it accomplished the feat of flattening space so effectively, and why a brief exponential expansion has such a powerful influence on the curvature of everything. To truly appreciate how inflation makes the universe so flat, it helps to think in terms of scale and perspective. Consider standing on a vast plain that stretches out as far as you can see. To your eyes, the ground looks perfectly flat and level in every direction, even though you know the Earth is a curved sphere. The reason, of course, is that you're sampling only a tiny portion of the Earth's surface. Earth's curvature is gentle, and its radius large compared to your horizon, so the curvature is effectively invisible to you. Now imagine making the Earth even larger. Inflate it like a balloon to 10 times its size, 100 times. The patch of ground you stand on would seem even flatter. If the Earth were expanded to an infinite size, any local patch would be completely flat because the sphere would become indistinguishable from a flat plane. This analogy captures what inflation does to the universe. It takes whatever curvature the young cosmos might have had and blows the universe up so huge, so quickly, that the part we can observe becomes essentially flat. Inflation's rapid expansion can be quantified in E-foldings, a term scientists use to count how many times the universe effectively doubled, or grew, by a factor of the mathematical constant E in size during that era. Even a modest number of E-folds, say 60 or so, is enough to expand the universe by a factor of around 10 to the 26th power. This kind of growth means that any initial curvature, whether the universe started a bit closed, like a sphere, or a bit open, like a saddle, gets stretched so enormously that its curvature radius becomes trillions upon trillions of times larger than our observable universe. To us, with our limited view, that original curvature is practically invisible, just as the Earth's curvature is invisible to someone looking at a small patch. Inflation, in effect, diluted the curvature. The more it stretched, the flatter the observable portion became. Imagine space as a rubber sheet that might have a slight bend or bump initially. Inflation pulls that sheet in all directions ferociously. Any bump or bend gets ironed out as the sheet becomes larger and larger. By the end of inflation, that sheet looks perfectly flat over the region we can access. In technical terms, the total density of the universe, the sum of all matter, radiation, and energy, gets driven very, very close to the critical density that marks the boundary between open and closed universes. Inflation naturally drives this sum to equal exactly 1, with any deviation exponentially suppressed. That is another way of saying space becomes flat. Even if the universe started with a significant curvature, after inflation you'd have to look unimaginably far beyond the observable horizon to even notice any residual curvature at all. It's remarkable that inflation doesn't require the universe to begin flat. It makes the universe flat, or extremely nearly so, regardless of how it began, as long as inflation lasted sufficiently long. One could say that inflation is a sort of cosmic forgetfulness for curvature. Whatever spatial curvature existed before, whether space was crumpled, curved, or looped, is essentially erased within the observable patch. All that remains is an almost Euclidean geometry. Think of it like the zoom-out effect on a rough image. Zoom out far enough, and even a jagged line looks straight. Similarly, inflation zoomed out the cosmic fabric so much that any warp or curve straightened to our sight. The concept of enough inflation is important. If inflation had been too short, say only a few doublings, the universe might not have expanded enough to hide curvature completely. But theory and some evidence suggest inflation, if it occurred, likely went on far longer than the bare minimum needed to solve these problems, essentially guaranteeing flatness to a precision we have yet to even measure. In fact, inflation predicts that the universe should be flat to a precision of many, many decimal places, more precise than any current observation can test. This means that even if there is a slight global curvature, it would be so tiny that it remains undetectable within our observable cosmos. This built-in flattening feature of inflation was one of its great triumphs. When scientists discovered in the late 1990s and early 2000s that the cosmic microwave background and galaxy distributions indicated a flat universe. It was a satisfying confirmation. Inflation's broad brushstroke seemed to match reality. The universe didn't have to be born miraculously balanced. It could have been nudged into balance by this early exponential stretching, by dramatically increasing the volume of space. Inflation watered down any exotic spatial curvature or any concentration of exotic relics and irregularities. After inflation, what was left was an almost pristine, flat universe, dominated by the inflating field's energy, with only the gentle ripples of quantum seeds breaking the perfect symmetry. However, inflation's gift of flatness came at a cost, at least temporarily. It left the universe in an extremely peculiar state. Space was essentially emptied out and chilled by the massive expansion. Any particles or radiation that had been around were stretched and diluted to negligible levels, like a drop of ink spread thin in an ocean. The inflating vacuum dominated everything, and as inflation ended, the universe was flat and smooth, but almost entirely devoid of the hot soup of particles and radiation we normally associate with the youthful universe. In a sense, inflation solved one set of puzzles by flattening and smoothing space. But now we face a new question. After such a blowing up and cooling down, How did the universe get all its matter and radiation back? How did this cold, empty, flat universe ignite into the hot Big Bang state that eventually led to stars and galaxies? The answer lies in what came next, a process known as reheating, the moment when the incredible energy-driving inflation was released, filling space with light and particles once more. When the brief epoch of inflation came to an end, it did not do so quietly. All the tremendous energy that had driven space to expand so feverishly had to go somewhere. Inflation's end was like the grand finale of a cosmic fireworks show, a release of pent-up energy that would ignite the next chapter of the universe's story. In those final moments, the inflaton field that had dominated everything began to oscillate and decay, transferring its energy into a shower of newly created particles and radiation. In an instant, the cold, empty expanse left by inflation was filled with a blazing flood of matter and light. This crucial transition is poetically called reheating. It is exactly what it sounds like. The universe, which had been chilled by its rapid expansion, was heated back up. In that moment, space was suddenly filled with the particles and radiation that would form all the cosmic ingredients we know today. Before reheating, during inflation, space was almost devoid of the familiar particles. No protons, no photons zipping around, no plasma, just the energy of the inflationary field, smoothly spread and doing its work of expansion. Space was essentially a cold vacuum dominated by this field. The temperature of any ordinary substance, had it existed, would have been driven down to near absolute zero by inflation's relentless stretching. But as inflation stopped, the enormous reservoir of energy locked in that field was suddenly liberated. One might envision a field of snow melting under a rising sun, turning into a gush of water. Similarly, the inflaton field melted its energy into a hot, dense broth of particles. The universe went from essentially empty vacuum to an extremely hot, dense state in a blink. It was a metamorphosis of pure energy into matter and radiation on a cosmic scale. During reheating, the temperature of the universe likely soared to stupendous levels. Incredibly, it may have been as hot or hotter than at any other time after the Big Bang, reaching into trillions of degrees. All that energy produced a primordial fireball of particles, matter-antimatter pairs, gauge bosons, quarks and gluons, everything jostling in a high-energy soup. Essentially, the conditions after reheating were those of the classic hot Big Bang fireball, as if inflation had prepared a perfectly smooth stage and then lit the lights. From this point onward, the universe's evolution proceeded as in the standard Big Bang picture. As it expanded and cooled, that hot particle soup thinned out. Within minutes, protons and neutrons fused into helium nuclei alongside hydrogen. Hundreds of thousands of years later, atoms formed, and gravity eventually gathered matter into the first stars and galaxies. In this way, reheating served as the bridge between the new idea of inflation and the well-established narrative of the Big Bang. We can think of inflation as having cleared and reset the stage, smoothing space and wiping away old clutter, and reheating as the spectacular opening act where the stage is set ablaze with activity. The warmth after the rush was in a sense the true beginning of the universe as we know it. If someone were watching this cosmic play unfold, inflation would have looked dark and empty. Despite all that exponential growth, nothing to see, no light. But reheating would be the moment the lights come on, the moment everything familiar is born from the vacuum. It's a dramatic thought. All the particles that now make up galaxies, stars, planets, and us were created from the decay of the inflationary field's energy at that primordial instant. In that sense, we are all children of inflation's afterglow. The details of reheating are complex and still an area of active research. Physicists use models to describe how the inflaton field decays, perhaps into heavy particles that in turn decay into lighter ones, a cascade that rapidly populates the universe with the full zoo of particles. There might have been brief periods of chaotic oscillations and rapid particle interactions, as the universe went from vacuum-like conditions to a hot plasma. It's almost like the universe had been straining under tension during inflation, and then suddenly relaxed, with that tension energy converting into heat. This enormous injection of energy likely overshot into a highly excited state, and then quickly thermalized, meaning particles collided and shared energy until everything settled into a uniform temperature distribution once more. After a short while, perhaps a fraction of a second or less, the universe achieved a hot, dense equilibrium, and the familiar expansion resumed, albeit now at a much calmer rate than during inflation. With the universe refilled with matter and radiation, the stage was set for all the structures to eventually form from the tiny imprints left by inflation. The nearly flat and smooth cosmos now contained all the ingredients it needed, and thanks to the seeds from quantum fluctuations, those ingredients were not spread perfectly evenly, ensuring gravity could start sculpting the cosmic landscape. The flatness remained. Space was still geometrically near perfect on large scales, but it was no longer empty or inert. It was a dynamic, glowing cauldron of possibility. Reheating is essentially the moment the Big Bang's classical hot era truly begins. Some have said that inflation replaces the bang in the Big Bang. It was this violent expansion and then reheating that provided the bang's energy and heat. Once reheating happened, the universe's evolution proceeded along lines we understand rather well. Cooling, expansion, formation of basic nuclei, then atoms, then the emergence of the first stars, after hundreds of millions of years, and so on. What inflation and reheating added to this picture was an explanation for why that hot beginning was so uniform and yet seeded with just the right imperfections. By tying up the loose ends of the inflationary story with reheating, we see a complete narrative from an initial burst that flattens and smooths everything to a handoff into the standard cosmic timeline. It's a beautiful idea, but it's important to remember that it is still a theory, albeit a widely supported one, about events at energies and times far beyond direct experimentation. Naturally, scientists have pondered, is this truly how it happened? Could there be alternatives to this dramatic inflationary beginning? And if so, how would those alternatives imprint the universe's geometry and structure differently? In the soft light of theory, several other ideas have emerged, offering different dawn-of-time scenarios that try to achieve some of the same feats as inflation without an initial bang-like expansion. While inflation has become the leading story of our cosmic origins, it's not the only tale in town. A few visionary cosmologists have explored alternative beginnings, scenarios where the universe's smoothness and flatness emerge not from a brief blast of exponential expansion, but through other, more subtle paths. These are the quiet alternatives at the dawn of time, models in which the Big Bang wasn't an explosive expansion from nothing, but rather a transition from a previous cosmic state. Among these ideas are bouncing cosmologies and the evocatively named ekpyrotic universe. Each paints a very different picture of the universe's earliest moments, yet they aim to solve the same puzzles of flatness and horizon in their own gentle way. In a bouncing cosmology, the universe may have undergone a cycle, a prior period of contraction that reversed into expansion, like a cosmic heartbeat. Instead of everything beginning from an infinitely small point, Imagine the universe had previously expanded, perhaps for an eternity, and then slowly begun to contract under gravity. During the contraction phase, as volumes shrink, densities and temperatures would rise. The hope in such models is that as the universe contracts, certain effects might smooth out irregularities and drive the cosmos towards a uniform, flat state. By the time the crunch reaches its smallest point, not a singular point of infinite density, but maybe a very high but finite density. The idea is that new physics causes a bounce. The contraction halts and turns into expansion, a new Big Bang of sorts, but one seeded by the remnants of the old universe. The bounce could be a singular event, or part of an eternal cycle of universes breathing in and out. It's a grand vision, a universe that has no true beginning, just endless cycles, each bounce refreshing it. The ekpyrotic scenario, on the other hand, comes from a different inspiration, one rooted in high-dimensional theory. The term ekpyrotic is derived from an ancient Greek word for conflagration, or cosmic fire. In this model, our universe's beginning was not a random singular explosion, but the result of a collision or interaction between two enormous membranes, branes, floating in a higher dimensional space. Before the collision, our universe-to-be was slowly contracting in a very smooth, controlled way under the influence of a special kind of energy field. That slow contraction, called an ekpyrotic phase, has a counterintuitive property. It smooths and flattens space, much like inflation does, but in reverse. As the universe contracts very gradually, any bumps or curves get ironed out because regions that are too curved or irregular collapse earlier, leaving behind only the smooth, flat background by the time the final crunch happens. Then, when the branes collide, essentially our Big Bang, their kinetic energy converts into the hot matter and radiation of the new expanding universe. The result is a cosmos just as flat and smooth as inflation would have made it, but achieved without a superluminal expansion. Instead, a slow, ultra-long squeeze beforehand did the trick. For supporters of the ekpyrotic model, this provides an elegant alternative to inflation's more explosive start. Both bouncing and ekpyrotic scenarios share a compelling trait. They attempt to solve the same fine-tuning puzzles as inflation, but with different cosmic choreography. In these models, the abrupt flash of inflation is replaced by either a gentler process, like a slow contraction leading to a bounce, or even a time before our bang, like a previous cosmic cycle. Yet the outcome can be strikingly similar. The universe emerges flat and smooth. In a bounce, for instance, if the cosmos was very large and nearly flat before contracting, it would emerge nearly flat after the bounce as well. Curvature wouldn't have a chance to grow significantly if, say, an ekpyrotic phase during contraction kept things homogeneous. The ekpyrotic slow contraction explicitly flattens the universe by dominating it with a special kind of energy that dilutes curvature, an uncanny mirror to inflation's method of flattening via expansion. So when you come out the other side of these alternative beginnings, you still have a universe that looks a lot like what we observe. Very nearly flat space with tiny seeded variations. However, these serene alternatives also have to explain the seeds of cosmic structure. Inflation's quantum fluctuations provide a ready mechanism for that. But what about a slowly contracting universe? Interestingly, even in a bounce or ekpyrotic scenario, quantum fluctuations can play a role, occurring during the contraction and surviving through the bounce to become the seeds in the new expansion. The details differ. For example, an ekpyrotic contraction might suppress many kinds of fluctuations, except those in certain fields, requiring more complex setups to generate a nearly scale-invariant spectrum of perturbations, the kind we see imprinted in the CMB. It's a delicate balance to get these alternatives to yield the same rich, successful predictions that inflation does. Some models have been crafted to do exactly that, at least on paper, producing a universe that looks almost indistinguishable from an inflationary one in terms of the patterns we observe today. Yet, almost indistinguishable hints at a crucial point. Perhaps there are subtle distinctions, faint fingerprints that could tell us which origin story is true. The different dynamics, a rapid outward stretch versus a slow squeeze and bounce, can imprint different traces. For example, a dramatic burst of inflation generally would produce a background hum of gravitational waves, ripples in spacetime from that violent expansion. A slow ekpyrotic contraction, by contrast, tends to produce far fewer gravitational waves, essentially a nearly silent gravitational signature. In a bounce, if the contraction was gentle, there may also be little in the way of strong gravitational wave relics. These primordial gravitational waves, if present, would leave an imprint on the very earliest light of the universe, particularly in the polarization pattern of the cosmic microwave background. Thus, even the quiet alternatives offer us a way to possibly distinguish them from inflation. By listening for the whispers of gravitational waves or the lack thereof. To test these ideas, cosmologists have turned their attention to the sky, searching in the cosmic afterglow for those ultra-subtle polarization patterns, the faintest of whispers that might reveal whether the universe inflated in a roar or bounced in a whisper. High in the Atacama Desert, at the South Pole, and in other remote, quiet corners of the world, telescopes have been scanning the heavens for some of the most delicate signals our universe has to offer. These signals aren't images or ordinary light, but subtle patterns in the polarization of the cosmic microwave background, patterns that could carry messages from the dawn of time. Polarization is a property of light, describing the orientation of its waves, and the cosmic microwave background, the afterglow of the Big Bang, is polarized at roughly the 5% level. This polarization arose when the first atoms formed and light was freed to travel. Photons scattering off electrons in that era acquired a faint preferred direction. It's in these faint directional patterns that the whispers of primordial gravitational waves might reside, like hidden music in a familiar song. There are two distinct patterns that cosmologists look for in the CMB's polarization map. One is called the E-mode pattern, which is more like a radial or flower-like design around hot and cold spots. This has been detected clearly and comes mainly from the ordinary density fluctuations, the same ones that gave us galaxies. The other is the elusive B-mode pattern, a kind of swirling or twisting pattern. Picture little whirlpools in the polarization directions. B-modes are much fainter and can be generated by two known sources. One, as a secondary effect, when E-modes get distorted by intervening matter, gravitational lensing, and two, potentially by gravitational waves rippling through the plasma of the early universe. It's this second source, primordial gravitational waves, that has drawn so much attention. Inflation, with its violent expansion, would have created a sea of gravitational waves, faint echoes of the universe's expansion, stretching and squeezing space. These would imprint a telltale swirl in the polarization pattern from the last scattering of light. In essence, inflation's roar would leave a whispering imprint on the sky, a swirl pattern that we can try to detect billions of years later. For cosmologists, detecting that swirl would be like hearing a message from the dawn of time, a confirmation of inflation's tremendous upheaval. The search for primordial B-mode polarization is like trying to hear a faint melody under a noisy background. The signal, if it exists at detectable levels, is extremely subtle, maybe only 1 part in a million of the total temperature fluctuations. Yet, it holds immense significance. A detection would be almost like seeing the Big Bang's fingerprint, evidence that inflation indeed sent gravitational tremors through spacetime. Conversely, not finding them, above a certain threshold, could hint that either inflation happened at energy scales too low to be easily seen, or perhaps that a scenario like the ekpyrotic one, which predicts a much weaker gravitational wave background, might be closer to reality. So far, the universe has guarded this secret closely. In 2014, there was a moment of electrifying excitement when a team announced they had spotted the swirling pattern of B modes at the South Pole's BICEP 2 telescope. It was as though a whisper from the dawn had been heard. But soon, that excitement sobered. Further analysis showed the signal was likely due to dust in our own galaxy, mimicking the cosmic whisper. The cosmos wasn't giving up its answer so easily. Since then, ever more sensitive experiments have continued to listen. They tune out noise, subtract interference from interstellar dust and galactic emissions, and push the limits of technology, superconducting detectors, ultra-cold sensors, all to detect this faint polarization pattern. The Planck satellite and ground observatories have measured lensing B modes, the kind caused by intervening cosmic structures bending light, and those measurements themselves enrich our understanding of the cosmos. But the primordial B modes, if any, remain at or below the current threshold of detection. What has been gleaned is that if inflation produced gravitational waves, their amplitude is below a certain level, often expressed as a ratio of power in gravitational waves to density fluctuations, denoted R. With current data, R must be less than on the order of 0.06 or even lower, meaning any gravitational wave whisper from inflation is very faint indeed. Still, the quest continues. New telescopes, arrays of detectors in high-altitude balloons, and even proposals for lunar observatories are in the works to listen more carefully than ever. It's poetic to think that our universe's beginning might still echo across the sky in polarization, not in light we see with our eyes, but in the orientation of that light. Each possible origin story has a slightly different expected whisper. A classic high-energy inflation might have left a relatively loud gravitational wave melody, within reach of detection soon, some hope. A lower energy inflation, or a gentle ekpyrotic bounce, might have left only the quietest of notes, maybe too soft for any realistic experiment to ever hear. Either outcome is profoundly informative. Hearing the B mode whisper loudly would vindicate the inflationary theory in a dramatic way, giving us a direct window into physics at unimaginable energies. Hearing only silence, or only the murmurs of lensing and galactic dust, would push us to rethink, perhaps giving more credence to those alternative, quieter cosmic origin tales. Beyond gravitational waves, polarization holds other clues too. It has informed us about when the first stars formed through a feature called the Rayonization bump in the E-mode polarization spectrum, and has helped refine our measurements of the universe's age and composition. But here, our focus is on that most hushed communication, the potential signature of primordial gravitational waves. It really is a whisper from the beginning. If inflation happened, the wave it rode could be sending us a message across time. Decoding that message is one of the most delicate tasks in cosmology today, requiring patience and ingenuity. As we await a definitive answer from the polarization data, we are reminded that our picture of the universe's first moments is still based on inference and circumstantial evidence. Inflation is compelling because it explains so much that we see: flatness, horizon, the pattern of galaxy seeds. Yet without a direct smoking gun detection like primordial B modes, some mysteries remain. We have these clues, these whispers, but not a full conversation with the cosmos's birth. Still, each incremental improvement in our observations sharpens the picture. And as that picture sharpens, we find that our universe is looking ever more flat, consistent with inflation's predictions, though it still leaves open the slightest possibility that maybe, just maybe, the universe's shape could deviate from perfect flatness. Despite the overwhelming evidence favoring flatness, scientists are careful to say the universe is nearly flat, not absolutely flat, at least, not yet. There's a reason for that cautious phrasing. Our measurements, as precise as they are, still have uncertainties and rely on certain assumptions. When we say the universe is flat, we mean that given our best data, from the CMB, galaxy surveys, supernovae, etc., the overall curvature appears to be 0 to within a small margin of error. But small is not 0. That margin currently allows for the possibility that space could have a slight curvature that we haven't detected, either curving very gently outward, open, or inward, closed, on scales just larger than what we can observe. It's a bit like declaring a tabletop perfectly level after using a level tool. You might say it's flat, but maybe if you looked with an even more sensitive level, you'd find a tiny tilt. For now, if the universe does have a curvature, it is so slight that the curvature radius would be at least dozens of times larger than the observable universe. In practical terms, that means any deviation from flatness is too small to show up in our sky maps and distance measurements with high confidence. One challenge in pinning down curvature is the entanglement with other cosmic ingredients. The geometry of the universe is determined by the balance of mass-energy density versus the expansion rate. We infer flatness by fitting our data to models that include components like dark energy, dark matter, and normal matter. If our understanding of one of those components is a little off, it could mask a small curvature or mimic one. For instance, the effect of a positive curvature, a closed universe, on the CMB can be somewhat similar to the effect of having a slightly different amount of dark energy or a different expansion rate. This is what scientists call a parameter degeneracy. Two different sets of conditions can produce very similar observational results. So, if we assume a certain value for the dark energy density or its properties and force flatness, we get one fit. If we relax that assumption, we might find a solution with a tiny curvature and a slightly adjusted dark energy that fits nearly as well. It becomes a game of precision and assumptions. With current data, the simplest fit, assuming the standard cosmological model, with a cosmological constant as dark energy, yields a curvature that's extremely close to 0. But in 2019, for example, the Planck satellite's analysis of CMB data alone showed a curious slight preference for a closed universe, just a few % deviation from flatness, though it was not statistically significant, and it conflicted with other observations like galaxy clustering and supernova distances. Most experts suspect that was a fluke or a result of unaccounted systematic effects, but it illustrates how tricky this measurement can be. That episode caused a stir at the time, ultimately reinforcing the need for multiple lines of evidence to cross-check cosmic curvature. Another fundamental limitation is the size of our observable universe itself. We can only see so far, about 46 billion light-years in radius, and that horizon is like our surveying limit. If the universe's curvature radius is much larger than that, our observable patch would look almost flat, no matter what. It's like trying to determine if the Earth is curved by walking around in your backyard. Your yard is too small relative to Earth to reveal the planet's roundness. Similarly, the only way to truly know if the universe is curved is to observe a significant fraction of the entire thing, which we simply cannot. We only have one universe and one vantage point, so we rely on subtle clues. We look for signs like if triangles formed by faraway galaxies have angle sums deviating from 180 degrees, or if distant volumes seem magnified or distorted in odd ways. So far, all these tests are consistent with flat geometry to the precision of our instruments. but the possibility of a slight curvature. Say, that space is very gently curved, so that if you could travel billions of light years beyond our horizon, you might eventually loop around, is not entirely ruled out. In cosmic measurements, even a tiny curvature has to compete with all the other effects. Dark energy, especially, dominates the universe's dynamics today and can mask curvature effects. A universe with, for instance, 98% of the critical density, slightly open, could be observationally hard to distinguish from one with 100% if you allow a little tweak in the dark energy behavior. And if dark energy itself isn't a simple constant, but something more exotic, our standard inference of geometry could be skewed. Scientists are trying to tighten these bounds. Upcoming galaxy surveys, better measurements of cosmic expansion, and more detailed CMB observations aim to constrain curvature to the order of per mil, thousandths of the total, or even per 10,000ths. But there will always remain a small window of uncertainty, partly due to that horizon limit, and partly due to the possibility of unknown factors. It's intriguing to consider what even a slight curvature would mean. If the universe is ever so slightly positively curved, closed, then on scales far larger than what we can see, space might eventually close back on itself, like the surface of a sphere. In such a case, the universe would be finite in volume, though extremely vast. And if you travelled in one direction long enough, far beyond what's possible now, you could in principle return to your starting point. If, on the other hand, it's slightly negatively curved, open, space would be infinite, curving outward in a saddle-like way, but even that curvature would be hard to notice locally. A perfectly flat universe, in the simplest topology, is infinite as well, stretching endlessly like an infinite grid. However, even a flat universe could be finite if it has a multi-connected topology, like a three-dimensional torus, wrapping around in ways that are hard to detect. Another wrinkle in the shape story. So flat doesn't automatically settle the question of infinite versus finite. That's something observational evidence has not decisively answered yet. In our current best understanding, almost flat is the state of affairs, and it might be the final answer. The universe could truly be flat and infinite. Many take inflation's success and the sharp agreement with flatness as a hint that the universe really is flat to all practical extents. But science remains cautious. We keep testing, because history has taught us that nature sometimes hides surprises in the margins of error. Perhaps with even more sensitive observations, we'll either shrink those error bars further, or one day detect a tiny divergence that tells us the universe does have a curvature after all. For now, we live with an awe-inspiring possibility. The universe is so vast and so finely balanced that it appears flat across all the billions of light years we can survey. Whether it is perfectly flat and stretches on forever, or subtly curves back on itself on the grandest scales, remains an open question. The distinction might seem academic when the curvature is so small, but it touches on the fundamental nature and fate of the cosmos. Is it infinite or finite? Will it expand forever? Is space unbounded, or does it eventually close? These profound questions ensure that the quest to determine the universe's true shape isn't over. It reminds us that even a nearly solved riddle can hold surprises, motivating astronomers to keep probing. As our journey through the cosmos continues, we carry forward the curiosity and tools to peel back more of the mystery. Each new observation brings us one step closer to understanding whether the cosmos is truly flat or has hidden curvature. The horizon beckons us onward, promising answers beyond. Those answers remain just out of reach, but we strive to find them, even if we must infer their truth from the subtle clues the universe has left in the sky. The night sky that once appeared as a scattering of isolated stars has given way to a grander vision, a cosmic map filled with galaxies. Over decades of careful surveying, astronomers have captured the positions and distances of millions of galaxies, transforming points of light into a three-dimensional atlas of the universe. In these maps, the galaxies are not randomly strewn about. They trace out patterns, immense clusters, elongated filaments, and vast, nearly empty voids. Each galaxy's position and redshift becomes a thread in a cosmic tapestry, revealing structure on scales almost too large to fathom. The result is a panorama of the cosmos that is both beautiful and scientifically rich, a portrait of how matter is arranged across space and time. In the beginning, though, everything was far more uniform. The early universe is thought to have been remarkably smooth, with only tiny variations in density. Over immense spans of time, those slight density differences grew under gravity's pull, forming a vast web of matter. Denser regions drew in more material and became the seeds of galaxies and clusters, while less dense regions emptied out into huge voids. Today, billions of years later, we see the outcome of that process. A cosmic web of filaments and sheets stretching across the observable universe, intricately woven by gravity. Galaxy surveys allow us to see this large-scale structure directly, a network of matter that forms the backbone of the universe. Early galaxy maps, though modest by today's standards, gave the first hints of this architecture. In the late 20th century, astronomers plotted the positions of a few thousand galaxies and discovered immense structures like the Great Wall, a sheet of galaxies hundreds of millions of light-years long, and giant voids nearly empty of galaxies. These were astonishing glimpses of order on gigantic scales. As technology advanced, survey projects grew vastly more ambitious. The Sloan Digital Sky Survey, SDSS, one of the most influential efforts, set out to chart a huge swath of the sky in unprecedented detail. Using a dedicated telescope, SDSS gathered precise images and spectra, measuring distances via redshifts to galaxies and quasars by the hundreds of thousands. Over its phases, SDSS mapped roughly 1 million galaxies in 3D space. Picture that. 1 million galaxies, each pinpointed in space, collectively outlining the cosmic web in our corner of the universe. At the time, this was a revolutionary achievement. 1 million redshift measurements, 1 million landmarks in the cosmic sea. And the pace only quickened. Newer surveys and instruments have pushed these numbers dramatically higher. One example is the Dark Energy Spectroscopic Instrument, DESI, which has taken the baton from earlier projects. Mounted on a telescope in Arizona, DESI uses 5,000 robotically controlled optical fibers to measure galaxy spectra en masse each night. Within its first year of operations, DESI compiled a 3D map containing over 13 million galaxies, the largest such map to date. Each of those galaxies has a measured redshift, indicating how much the universe has expanded since the galaxy's light was emitted, effectively giving its distance. With tens of millions of mapped galaxies, astronomers can trace the filaments and voids with exquisite precision. It's as if we have taken a rough sketch of the cosmic web and refined it into a high-resolution drawing, extending billions of light-years in extent. The patterns we see in this map are the imprint of eons of cosmic history. These grand surveys do more than satisfy our curiosity about what the universe looks like. They turn those patterns into precise measurements of cosmic scale. One of the most important is something called baryon acoustic oscillations, often abbreviated as BAO. This mouthful of a term refers to a faint but distinctive pattern. Galaxies are very slightly more likely to be separated by a particular distance, about 500 million light-years, than by other distances. This preferred scale is a relic of primordial sound waves that travelled through the hot plasma of the young universe, leaving behind an echo in the later clustering of galaxies. In essence, it's as if galaxies, on average, tend to form on the expanding spherical shells of those ancient sound waves. The result is a cosmic standard ruler embedded in the distribution of galaxies. By surveying millions of galaxies and measuring how they cluster at various separations, astronomers can pick out this BAO signal, a slight excess of galaxy pairs at that magic separation. Once they identify the feature in the data, it serves as a yardstick for cosmic distance. It reveals how far apart those galaxies truly are in space, allowing cosmologists to gauge the scale of the universe at that epoch. The actual physical length of the BAO ruler, about 490 million light-years in today's universe, is known from the physics of the early universe. If the universe's expansion history had been different, that standard ruler would appear at a different angular size than expected. In a very curved universe, for instance, the ruler's apparent size would be subtly different compared to a flat cosmos. Astronomers look for just such differences. By comparing the observed BAO imprint at various distances to its known true size, they can see how the expansion has changed and whether space is flat or not. This approach makes BAO a powerful probe of cosmic geometry. This technique of using galaxy patterns has delivered the most precise measurements in cosmology. For example, the Baryon Oscillation Spectroscopic Survey, BOSS, mapped 1 million galaxies and determined the cosmic distance scale to 1% accuracy. Such precision has sharpened our knowledge of how fast the universe expands and how much dark energy is required to drive that expansion, combined with measurements of the cosmic microwave background and distant supernovae. The BOSS results support the idea that dark energy is a cosmological constant, an unchanging energy density in space. Notably, BOSS also provided one of the best measures of spatial curvature. The answer, essentially, is that space is nearly flat, or as the survey team put it, not curved much. Astonishingly, the diverse cosmic probes we have explored, from the gentle clustering of galaxies to the faint distortions of distant light, all paint a broadly consistent picture. They converge on a simple, elegant model, a universe that on the largest scales appears flat in geometry and governed by dark energy and dark matter. The cosmic microwave background's echoes, the cosmic web's structure, the dimming of supernovae, the ripples in galaxy clustering, the subtle shear in galaxy shapes, and even the new gravitational wave measurements all weave together into a tapestry that largely agrees. It's a remarkable achievement of modern science that we can cross-check the shape and composition of the cosmos in so many independent ways, arriving at the same basic story. The cosmic web's tapestry is a mix of gossamer emptiness and dense knots. Imagine drifting in one of the immense voids, an almost unimaginable expanse with hardly a galaxy in sight, then coming upon a wall of galaxies, a great filament stretching across space. These voids and walls are the yin and yang of cosmic structure, vast regions nearly empty of matter, adjacent to crowded clusters and sheets of galaxies. By studying the sizes and distribution of voids and the mass of galaxy clusters, cosmologists effectively weigh the large-scale structure of the universe. The average densities in voids and walls, and the way they change over cosmic time, reveal how gravity and expansion have sculpted the cosmos. Over billions of years, the initially mild lumpiness of matter has amplified, dense regions growing denser, empty regions emptier, as gravity drew material inwards. A loose network of dark matter filaments gradually collapsed and grew clumpier under the relentless pull of gravity, confirming theories of structure formation. We see this in the present universe. Galaxies within clusters are bound tightly, while surrounding those clusters are giant voids that have emptied out as matter drained into the walls. It is as if the universe, over time, has sharpened the contrast in its structure. The rich get richer, the voids get larger. Observations of galaxy surveys at different epochs show that long ago, matter was distributed more evenly. As time went on, clusters became more massive and voids more pronounced. This growth of structure provides another test of our cosmological model. The amount and speed of structure growth depend on fundamental cosmic parameters, including the total amount of matter in the universe and the properties of dark energy that govern the expansion rate. By measuring how many galaxy clusters exist at various distances, hence times in the past, and how large the voids are, scientists can infer how the universe's expansion has either fostered or stunted the formation of structure. A faster expansion, for example, driven by an early burst of dark energy or a low matter density, would slow down the growth of clusters and allow voids to dominate, whereas a slower expansion or higher matter density would clump matter more quickly into walls and clusters. The real universe, as observed, shows just the right balance of these elements to be consistent with the same flat, lambda CDM cosmos that emerges from other lines of evidence. The distribution of voids and walls on the largest scales matches the patterns we expect for a universe with around 30% matter and 70% dark energy, exactly the proportions also indicated by the cosmic microwave background and supernova studies. The geometry of space comes into this as well. In a universe with significant curvature, the volume of space at a given distance would be different, which would change the observed number of structures of a given size. But surveys find that the counts of clusters and the expanse of voids as a function of distance are just what a flat universe model predicts. What about the very largest structures? Could they give away any curvature of space? If space were curved like the surface of a sphere, traveling far enough in one direction might eventually bring you back to your starting point, and we might see repeating patterns in the arrangement of galaxies. Astronomers have looked for such cosmic repetitions or unusual alignments on the grandest scales and haven't found any credible signs. As far as our maps reach, the cosmic web extends without obvious boundary, and its statistical properties remain uniform. This is in line with a flat, or extremely gently curved, infinite cosmos. If there is curvature, it is so subtle that even structures hundreds of millions of light years across do not reveal it. In essence, weighing the walls and voids, counting galaxies, measuring cluster masses, gauging the emptiness of voids, has added yet another vote of confidence that we live in a cosmos best described as flat and homogeneous on the largest scales. And, just as importantly, these studies show that our universe's structure has grown over time in the manner expected, further entwining the tale of geometry with the tale of cosmic evolution. Imagine looking at a distant galaxy through an immense cosmic window pane, one that is not perfectly smooth, but subtly warped by gravity. The light from that galaxy travels across billions of light years, passing by clusters of galaxies and clumps of dark matter, and those masses bend its path ever so slightly. By the time the light reaches our telescopes, the distant galaxy's image is distorted, stretched or sheared into a slightly different shape than it originally was. This effect is called weak gravitational lensing. Weak, because the distortions are tiny, like viewing a scene through gently wavy glass. Individual galaxies appear only marginally skewed, but by observing millions of galaxies, astronomers can detect coherent patterns in these subtle shape distortions. These patterns are a cosmic fingerprint of the large-scale distribution of matter, both visible and invisible, along the line of sight. In essence, every distant galaxy is a background light source, and the universe's web of mass between us and those galaxies acts like a giant lens. Regions with more mass, a galaxy cluster, say, or a dense filament of dark matter, will bend the light a bit more, causing background galaxy images behind them to be tangentially stretched. By statistically analyzing the alignments and shapes of many background galaxies, scientists can map where mass is concentrated in the intervening space. Remarkably, they can even chart the invisible. The vast majority of matter in those clusters and filaments is dark matter, which emits no light. Yet its presence is revealed through the gravitational stretching of galaxy images. Over huge patches of sky, this technique lets us build a kind of shadow map of the cosmic web. A map not of light, but of mass itself. In recent years, surveys have charted these weak lensing signals across large fractions of the sky, using tens of millions of galaxies as beacons. The result is a direct measurement of how matter, especially dark matter, is distributed on large scales, and how clumpy it has become over cosmic time. Weak lensing provides a powerful check on cosmic structure and geometry. The degree of shear, how much the images are distorted, reflects both the strength of gravity's pull, which depends on how much matter is present and clustered, and the distances involved between us, the lens, and the source. Because the bending of light depends on the relative distances, a different spatial geometry, for example, a universe with curvature, would alter the lensing patterns we observe across redshifts. Similarly, if dark energy causes the expansion to speed up, structures grow more slowly, affecting the amount of lensing. In a flat lambda CDM universe, simulations predict a certain level of correlated galaxy distortions on various angular scales. Observations have now measured these signals with high precision, allowing a comparison to theory. By and large, the weak lensing maps of the universe are consistent with a nearly flat cosmos and the level of clumpiness expected in the favoured model. Each new survey provides an opportunity to test that consistency more stringently. Interestingly, early results from several large lensing surveys hinted that the cosmos might be a touch less clumpy, that is, the dark matter fluctuations slightly smoother, than predicted by the CMB-based model. In technical terms, the parameter describing the amplitude of matter clustering, often denoted S8, came out a bit low. This prompted careful scrutiny. Could it be a sign of new physics, or merely a small unaccounted bias in the measurements? Over the past few years, as techniques improved and more data rolled in, the lensing results have shifted closer to the Planck CMB results. The latest wide-field studies find that the difference is not statistically significant, and the slight shear discrepancy may have been due in part to subtle issues in early data analyses. For now, weak lensing and other probes seem to be in harmony, each reinforcing the picture of a flat, accelerating universe. But even this exercise has been valuable. It reminds cosmologists to remain vigilant. The measurements are challenging. One must account for tiny instrumental biases, the intrinsic alignments of galaxies with one another, and the obscuring effects of intervening dust. The fact that independent surveys on different continents, and even in space, are converging on similar results builds confidence that we truly understand the whisper-light shear of the cosmos. And with new observatories on the horizon, from the Vera Rubin Observatory's Legacy Survey of Space and Time to the Euclid and Nancy Grace Roman space telescopes, the coming years will bring an even sharper view of these gentle distortions. Like a final polish on that cosmic window pane, they will reveal the universe's shape and structure with ever greater clarity, or perhaps unveil surprises that lurk in the background blur. It begins with a distant cosmic catastrophe. Two ultra-dense neutron stars spiraling in towards each other. As they merge in a violent flash, they unleash not only a burst of light, but also a tsunami of gravitational waves rippling through the fabric of space-time. These gravitational waves spread out in all directions, carrying a detailed record of the mass and motion of the merging stars. In 2017, detectors on Earth felt such waves wash over our planet for the first time from a neutron star merger. It was as if the universe rang a deep and distant bell, one that we could finally hear. What made this event even more remarkable is that telescopes caught the accompanying flash of light, a kilonova, and pinpointed the galaxy where it happened, about 130 million light-years away. In that moment, astronomers gained a powerful new tool for measuring the cosmos: a standard siren. Gravitational waves from events like this carry an imprint of their absolute strength. By analyzing the gravitational wave signal, how its frequency and amplitude change over time, scientists can determine the intrinsic energy and luminosity of the event. As the waves travel outward, they weaken with distance, much like the sound of a siren fading as it moves away. By the time the waves reach Earth, their strength reveals how far they have traveled. This makes neutron star mergers and similar gravitational wave sources into standard distance markers. The term standard siren is a nod to the better-known standard candle method using supernovae. But instead of a candle's light, we have the siren-like wail of spacetime vibrations, calibrated by the well-understood physics of general relativity. Crucially, this method does not rely on intermediate rungs of a distance ladder. It is a direct reading of distance from the universe's own gravitational whisper. When the distance determined from a gravitational wave event is combined with the redshift of the host galaxy, measured from its light spectrum, we get a point on the cosmic expansion curve, an independent measurement of the Hubble constant, or more generally, the expansion history. With the very first neutron star merger detection, scientists produced an estimate of the Hubble constant that intriguingly landed between the clashing values from other methods. The uncertainties were large. The error bars spanned both the Planck and local distance ladder results, but it demonstrated the principle. They have the potential to arbitrate the tension in H0. If multiple siren measurements consistently favor one value over the other, it could tip the scales on that debate, or reveal new physics affecting the expansion. Standard sirens also offer a novel probe of cosmic geometry. Just as with supernovae and BAO, a different spatial curvature, or an evolving dark energy component, would alter the distance redshift relationship. Gravitational wave sources at various distances can thus test whether our assumed cosmological model, flat lambda CDM, correctly predicts those distances. In principle, a network of many sirens spread across the sky and time could even detect slight departures from flatness or from the expected expansion rate, should they exist. And because these measurements don't rely on the brightness of objects, which can be dimmed by dust or affected by complex astrophysics, they come with different systematic uncertainties, providing a crucial cross-check. For now, the field of standard siren cosmology is just beginning. The handful of events detected so far are like distant beacons just coming into view. The LIGO and Virgo gravitational wave observatories have already expanded our awareness, detecting dozens of mergers, mostly black holes merging with black holes. Most of those have no light to identify their location and redshift, so their cosmological use is limited. But as detectors improve in sensitivity, the rate of detections will increase, including more neutron star mergers and perhaps black hole neutron star collisions that can be linked to visible galaxies. Planned observatories in the next decade, on the ground and in space, promise a flood of new sirens. Each will come with its own unique song of spacetime, and when we decode those songs, we'll be listening to the rhythms of the expanding universe itself. If the cosmos has more subtle curvature or unexpected tune changes in store, the sirens will help us hear them. And even if they confirm what we suspect, a flat, steadily expanding cosmos, they will have done so by an entirely new and marvelous means, adding a beautiful symmetry to our quest to measure the universe. The expansion of the universe is often likened to a cosmic flow. Galaxies carried apart like driftwood on a vast river of space. Measuring the speed of that flow, the Hubble constant, h0, has been a central quest for cosmologists. In recent years, a puzzling discrepancy has emerged in our measurements of h0, sometimes referred to as the Hubble tension. It's as if two separate sets of cosmic clocks are ticking at slightly different rates, and scientists are trying to figure out why. One method of measuring h0 relies on the local universe. Observing Cepheid variable stars and type Ia supernovae in nearby galaxies to calibrate distances, and then using those standard candles to gauge how fast galaxies are receding. This approach, carried out by teams such as the SH0ES collaboration, led by Adam Rees, yields a Hubble constant of around 73 kilometers per second per megaparsec. In essence, it suggests that for every megaparsec, about 3.26 million light-years of distance, the recessional velocity of a galaxy increases by 73 kilometers per second due to cosmic expansion. The other method draws on the very early universe. It uses measurements of the cosmic microwave background, for example, from the Planck satellite, and the standard cosmological model to predict what h0 should be today. That method consistently gives a lower value, around 67 kilometers per second per megaparsec. The difference between approximately 67 and approximately 73 may not sound like much, but the error bars on these measurements are small enough that the discrepancy is highly significant. In fact, on the order of 5 standard deviations in statistical terms, a level typically considered a discovery in physics. This situation has put cosmology in an intriguing bind. On one hand, the elegant lambda CDM model, with a flat universe, dark matter, and dark energy, has been spectacularly successful in matching data like the CMB and galaxy surveys. On the other hand, if that same model is extrapolated to the present, it appears to underestimate the current expansion rate compared to direct observations. Could there be something missing in our model? Perhaps new physics that changes the early expansion, and thus the CMB inference of h0? Or are we miscalibrating something in the local distance ladder measurements? Researchers are exploring both avenues with vigor. On the new physics side, ideas abound. One proposal is an extra injection of energy into the early universe, sometimes called early dark energy, that could make the young universe expand a bit faster, thereby reducing the inferred h0 from the CMB side without wrecking the fit to CMB data. Other possibilities involve novel neutrino physics, a small violation of the simplest form of dark energy, or even a modest curvature of space, a slightly closed universe, that was previously assumed to be zero. A slightly curved universe could in principle reconcile some of the tension, but it comes into conflict with other observations like BAO, so it's not a clear solution. Each of these hypotheses must pass a gauntlet of observational tests, and so far none has achieved consensus as the answer, but the door remains open. Meanwhile, on the astrophysical and calibration side, teams have been meticulously re-examining the local distance ladder. Could there be biases in how we measure Cepheids? Or perhaps the galaxies we've observed happen to reside in a region that's not perfectly average. For instance, maybe our local volume is underdense or overdense, skewing the h0 derived. Alternative distance calibrators have been employed, for example, using the tip of the red giant branch, TRGB, stars as standard candles instead of Cepheids. The TRGB method has yielded h0 in the upper 60s, somewhat bridging the gap, but still not fully erasing the difference. With the advent of the James Webb Space Telescope, Cepheid distances are being measured with higher precision and less interference from dust, and so far these measurements have upheld the previous local h0 value, rather than revealing a bias in the Hubble flow. This strengthens the case that the tension is real, not just an observational fluke. Thus, the Hubble tension stands as a gentle but persistent reminder that our understanding of the cosmos is not complete. It's a bit like hearing a faint disharmony in an otherwise beautiful symphony. It doesn't ruin the music, but it catches the trained ear. In response, cosmologists have grown both cautious and excited. Cautious, because it demands we double-check all aspects of our measurements. Excited, because history has shown that little discrepancies can herald big discoveries. At this point, we cannot say whether the H0 tension is the result of subtle biases or a sign of new cosmic truth. The resolution may come in the next few years, as we gather more data, for instance, from new supernova surveys, improved parallax distances from Gaia, or more standard sirens from gravitational waves. And as we refine our models, the universe will either bring its two clocks into agreement or show us something wonderfully new. Until then, the tension in the Hubble flow remains an open question, a scientific mystery unfolding in real time, urging us onward in the quest to understand our expanding universe. Every cosmological measurement comes tethered to a framework of assumptions, some explicit, some so ingrained they often go unmentioned. These assumptions act like the quiet stagehands of the cosmic drama, mostly unseen, but positioning the props and backdrops that set the scene for our interpretations. When we quote a result such as, "the universe is flat within plus or minus 0.1%, it is usually within the context of a specific model, say lambda CDM, and often under certain prior beliefs. For example, that space has no weird topology, or that there are 3 light neutrino species, and so on. Understanding how these priors and model choices shape conclusions is a vital, if subtle, part of modern cosmology. Take, for instance, the question of spatial curvature. If a research team assumes from the outset that the universe is perfectly flat, as many analyses do, based on strong prior reasoning from inflation theory, then naturally their final results will reflect that assumption, sometimes even quoted as, "we confirmed the universe is flat," when in fact flatness was built into the model to begin with. To truly test flatness, one must allow a model with curvature and see what the data prefer. When this is done, the data's answer can shift in intriguing ways. For example, the Planck satellite team found that if they did not impose flatness, their best fit CMB data alone showed a slight preference for a closed universe, positive curvature. This caused a stir, since it seemed at odds with other evidence. However, that result came with larger uncertainties and some tension with cosmic microwave background lensing data. Once other datasets like BAO galaxy distances were added as additional anchors, the overall analysis swung back to consistency with flatness. The prior belief and theoretical expectation of flatness was so strong that many scientists suspect the Planck closed universe hint was a statistical fluke or a result of unmodeled complexities. But it was a reminder that assuming something and measuring it are not the same. Beyond curvature, there are many other quiet assumptions. Are we sure dark energy has exactly the equation of state W equals -1 as a cosmological constant? Most analyses assume this in the base model. If we relax that and let W vary, the allowed range of other parameters can shift. The same is true if we allow more exotic possibilities, say an extra neutrino-like particle in the early universe, or a time-varying form of dark energy. These extended models can sometimes alleviate small tensions between datasets. One can always fit better by adding more parameters, but the cost is complexity and ambiguity. Too much freedom, and the data can no longer pin things down. There is an art to choosing a model. one tries to include enough flexibility to capture reality, but not so much that the picture becomes blurry and overfit. The lambda CDM model has been favored in part for its economy. With just a handful of parameters, it explains a wealth of observations. Yet we must remember it is nested within broader frameworks that we could explore if needed. Priors, too, play a key role. In Bayesian analysis, common in cosmology, one must input prior probability distributions for parameters before seeing the data. Typically, these priors are chosen to be broad and uninformative, meant not to bias the results. But sometimes, what one person calls uninformative might still influence outcomes. For example, a prior that restricts the Hubble constant to a narrower range could sway a combined analysis if one dataset is not very constraining. In recent years, cosmologists have been careful to test how sensitive results are to reasonable variations in priors. Generally, the big conclusions, like the universe is flat or dark energy exists, have proven robust. They don't vanish with a different prior or analysis method. That said, the smaller details, say the exact inferred value of a parameter like sigma 8 or the neutrino mass upper limit, can shift slightly under different assumptions, which is important when interpreting whether there is truly a tension or not. The phrase quiet assumptions also applies in a more philosophical sense. We all carry prior expectations, often born of theoretical elegance or past experience, about what the universe should be like. Inflation theory, for instance, elegantly explains why the universe's geometry should be flat, so most of us expected flatness even before it was measured. This can subconsciously influence how we approach analysis. It's noteworthy that for decades, some researchers made a point to actually fit curvature as a free parameter, especially before the era of precision data, and they kept finding it consistent with zero. Over time, this bolstered confidence in flatness and made setting omega k equals 0 a reasonable default choice. But one can ask, if the results had consistently come out slightly open or closed, would we have been as quick to bake flatness into our standard analyses? Probably not. Thus, it's healthy to occasionally step back and re-examine even our deeply held assumptions. In the end, handling priors and model choices is about transparency and testing. Cosmologists often perform analyses, both with and without certain assumptions, to see how conclusions differ. They report alternate scenarios. If we drop the flatness prior, here's what changes. Or, if we allow W not equal -1, here's how H0 shifts. This way, the community can gauge which insights are solid and which hinge on a particular framework. Far from being a weakness, this practice is a strength of the field. It's how we ensure we're not fooling ourselves. As the saying goes, extraordinary claims require extraordinary evidence, and part of that evidence is showing that a result holds up under varied assumptions. In the quiet turning of dials and toggling of model parameters behind the scenes, cosmologists are essentially asking the universe, are we seeing this right, or are we colouring by our own preconceptions? So far, the universe, in its consistent answers across experiments, has been reassuring, but also a little playful, leaving just enough anomalies to keep us wondering if a new paradigm shift might be waiting in the wings. In the grand quest to measure the cosmos, even a ray of starlight can carry hidden biases. Nature, and our instruments, introduce small twists. A bit of dust here, a slight detector quirk there, that can quietly skew results if we're not careful. These subtle sources of error are collectively called systematics, and dealing with them is a bit like chasing shadows. They do not blare their presence. Instead, they gently tug at the data, bending an inference by a few percent. But in cosmology, a few percent can be the difference between a revolutionary discovery and a mere mirage. That's why scientists devote as much effort to characterizing and eliminating systematics as they do, to collecting the data in the first place. Consider, for example, the dimming effect of cosmic dust. When we observe a distant supernova, we assume that its faintness is due to distance. The farther it is, the dimmer it appears. But interstellar dust along the line of sight can also dim the light, making a relatively closer supernova look farther than it truly is. Unless one corrects for dust extinction, using the supernova's color information or other indicators, one might systematically overestimate distances. For the studies of dark energy via supernovae, this was a major concern. Are these distant supernovae truly fainter because of acceleration, or just dustier? Fortunately, through careful, multi-wavelength observations and calibration, astronomers learned to account for dust, and the conclusion of accelerated expansion remained intact. Still, dust is a constant companion in precision astronomy, especially when comparing optical measurements, more affected by dust, with infrared ones, which James Webb Space Telescope and others use to pierce through dust more effectively. Another subtle bias comes from selection effects. Essentially, the fact that the easiest objects to observe aren't always typical. Imagine you're compiling a list of the brightest standard candles in distant galaxies. Naturally, you will tend to catch the most luminous examples, while fainter ones fall below your detection limit. This Malmquist bias means that your sample might be skewed towards intrinsically brighter objects, which, if not corrected, could make distant objects seem closer than they are, since you're comparing only the bright ones. Cosmologists correct for this by carefully modeling the detection efficiency and including the fainter objects when possible, or statistically accounting for those missed. Similarly, consider surveys of galaxies. A magnitude-limited survey will preferentially include the most massive, bright galaxies at large distances, possibly missing smaller ones. Without correction, one might infer an evolution in galaxy properties that is partly just a selection artifact. Calibration is another quietly critical systematic. This refers to the process of converting the raw signals we observe, like detector counts, into physical quantities, like fluxes, magnitudes, or redshifts. A small calibration error, say a 1% offset in the brightness scale of a telescope, can propagate into a 1% error in distance measurements. In the context of the Hubble constant or dark energy's equation of state, 1% is a big deal. That's why teams spend years refining calibration, comparing different instruments, using standardized sources, like specific stars or lab lamps, to make sure that a magnitude measured in one survey means the same as in another. The recent tension in H0, for example, has pushed calibration efforts to new heights. The SH0ES team, using Hubble Space Telescope data, took great pains to calibrate Cepheid brightnesses across different galaxies. Meanwhile, others looked at independent ways to calibrate distances, like the aforementioned TRGB method. When JWST arrived on the scene, it provided fresh eyes in the infrared, reducing uncertainties from dust and confusion in crowded fields. Encouragingly, JWST's early observations have largely confirmed the HST distance scale, rather than revealing a big calibration mistake, reinforcing that the H0 tension is not simply a mismeasurement. Each observational probe has its own menagerie of potential systematics. In cosmic microwave background experiments, one worries about instrumental noise patterns or foreground emission from our galaxy. The Planck team, for example, had to separate the CMB from diffuse Milky Way dust emission, a tricky business that, if done imperfectly, could bias the inferred cosmological parameters. They also had to account for the subtle frequency-dependent calibration of detectors. In large galaxy redshift surveys, systematics include variable depth of observations. Some patches of sky see fainter galaxies than others, fiber positioning errors, or even stars masquerading as galaxies. These can imprint artificial patterns that might mimic or obscure real cosmic signals. Thus, survey teams build detailed systematic maps, highlighting regions where, say, the observing conditions were poorer, and marginalize out or correct for those effects in their analysis. Weak lensing surveys have an infamous systematic. The shapes of galaxies must be measured with exquisite accuracy, but our atmosphere and telescope optics themselves blur those shapes. Calibrating the point spread function of a telescope, how a point source like a star is smeared out, is crucial. Any residual error can produce a false shear signal. Teams like those on the Dark Energy Survey and Kilo Degree Survey spend tremendous effort modelling the PSF across every exposure. Even the slight intrinsic alignment of galaxies with each other, from tidal forces during formation, is a systematic for lensing. It's a real effect, but not the gravitational lensing effect we're after, so it must be accounted for in the models. We saw earlier how the early weak lensing results had to wrestle with these issues, and improvements in controlling them partly resolved what looked like a discrepancy. In short, much of the invisible work in cosmology is battling these little gremlins of bias. The good news is that, by and large, different teams and different methods are converging on consistent results, which gives confidence that systematics are under control. It's often said that extraordinary claims require extraordinary evidence. One corollary is that extraordinary evidence requires extraordinary care. For the accelerating universe discovery, teams had to convincingly show that no known systematic dust, evolution, etc., could explain away the dimming of supernovae. And they did. For the Hubble tension, the scrutiny is ongoing. Each potential systematic in the Cepheid supernova route or the CMB analysis is being poked and prodded, and so far, a straightforward resolution has not emerged. This thoroughness is a feature of the science, not a flaw. It means that when a cosmological result is finally accepted, we know it has survived an onslaught of skeptical checks. And if something still doesn't add up, like two careful measurements disagreeing, it tells us we either haven't found the sneaky bias yet, or, tantalizingly, that new physics might be at play. Thus, systematics, those small biases in starlight and data, are not just obstacles. They are also clues. In tracking them down and understanding them, we often learn more about our instruments, our methods, and sometimes even about the universe itself. Stepping back, one can't help but be struck by how all these separate cosmic investigations interweave into a coherent story. The ancient light of the cosmic microwave background, the standard candles in distant galaxies, the clustering of galaxies, and the cosmic web, the graceful shear of space traced by lensed galaxies, and the new gravitational sirens. They all point to a universe that is remarkably well described by a simple model. In this model, space is overall flat, filled with about 30% matter, mostly dark, and 70% dark energy, and has been expanding for 13.8 billion years from a hot, dense beginning. Each new piece of evidence has added confidence to this picture. Like distinct musical instruments in an orchestra, these diverse observations have converged to play in harmony, giving us a grand cosmic symphony that sounds, for the most part, consistent and true. The success of this concordance model is a triumph of modern science. Not so long ago, the shape, size, and fate of the universe were matters of speculation. Now we can state, with quantitative certainty, that the universe is flat to within a tiny margin, and that its expansion is accelerating due to what we call dark energy. We've measured the cosmic expansion history from the primordial fireball to the present day using independent techniques and found the pieces fitting together uncannily well. It's a testament to human curiosity and ingenuity that we've come this far, from wondering if the universe might be a finite sphere or infinite plane. to mapping it out and finding it spatially uncurved as far as we can see. For many cosmologists, this concordance brings a sense of closure to questions that have lingered since Einstein's time. We set out to measure the shape of the universe, and the answer, flat, has emerged loud and clear. And yet, in that clarity, there is room for humility and wonder. We know our model is an approximation of reality, however splendid its victories. The threads of evidence have come together, but a few loose ends remain. The precise rate of the present expansion, the Hubble constant, measured locally, doesn't perfectly match the value inferred from the early universe. The reason why is still up for debate. The exact amount of clumpiness in matter observed via lensing appears just slightly less than that predicted by the CMB, hinting at something we might have overlooked. These could be minor issues, statistical flukes, or small systematics we have yet to nail down. Or they could be clues that the fabric of our model has richer patterns waiting to be revealed. We hold space for that uncertainty, recognizing that each time in history we thought we had the universe mostly figured out, nature had surprises in store. In this spirit, the work continues. New observatories and surveys are on the horizon, poised to refine or redefine what we know. The Euclid satellite and NASA's upcoming Roman Space Telescope will map galaxies and measure dark energy with unprecedented precision. The Vera Rubin Observatory will conduct a sweeping survey of the sky night after night, catching supernovae by the thousands and mapping gravitational lensing across vast areas. As these next-generation instruments come online, they will test our flat universe paradigm in even more detail. Perhaps they will simply tighten the error bars, turning our tentative dotted lines into bold ones, confirming that the geometry is flat and the concordance model holds strong. Or perhaps they will expose discrepancies that force a rethink, a gentle tension pulling at the tapestry of our cosmology that could unravel a new layer of truth. Either outcome is a gain in knowledge. For now, at the end of this multifaceted exploration, we see a picture of a universe that is immense, likely boundless, and governed by elegant but mysterious forces. It is flat in shape, which might imply it is infinite in extent, yet we cannot directly see beyond the horizon of our observable patch. It is expanding faster and faster, driven by a dark energy we have yet to comprehend. We find ourselves living in a truly remarkable cosmos, one that we've come to understand to a profound degree, and yet one that continues to beckon us with deep questions. In the cosmic loom, many threads have converged to form a clearer image, but the loom is still open. There is room to weave in new threads of discovery. As we move forward, guided by both our well-tested knowledge and our readiness for the unexpected, the shape of the universe will continue to come into sharper focus. And with each new observation, we participate in an ongoing act of cosmic understanding, a story, perhaps, with no final page, but rather an ever-unfolding journey under the canvas of the heavens.